Good morning, gentlemen.
Good morning.
We are starting our morning session. I have the honor of chairing this session. My name is Gemo Nicol from Sofia University. I was expecting at least one lady, the new elected dean of our faculty, but since she is busy, the new position means also new duties. So let me start with warning you that I know little about coding theory. Fortunately, there are bridges between my subject, approximation theory, and so what bridges the two branches are the beautiful extremal problems appearing in both. Actually, I see here people from who I consider members of approximation theory society, including director of Center on Approximation Theory in Vanderbilt, Professor Saf, and my friend and colleague Stuart Travis, who is frequent participant in our conferences on constructive theory of functions. So we are starting with 10 minutes delay. So we have to take from the continuous blog.
Thank you, Geno, for the introduction. And I'm very sorry for the technical difficulties which delayed the start of the lecture. So this lecture will be about a generalization of the Delsart or linear programming approach to packing type problems and estimating packing densities. Okay, first, just okay. So here is a literature which is related in my work. Some of them not published properly or in the preparation. Basically, there will be two main issues or topics in the lecture. One is a very general theorem, which I will present soon, and which is the main result of this paper which appeared in the Annali Pisa. And the other thing which is used there is basically the main technical tool which is necessary to formulate anything, and that is the notion of the density in locally compactable groups. So here is the main result. If you are familiar with all these packing things and Delsart bound and so on, then everything should be kind of familiar to you, except that I present everything in the setup of locally compactable groups. So H is a subset, say open, with compact closure. It's so important that it be bounded or compact closure. And lambda is a set of translations which defines a strict packing on the base set on the locally compactable group, which can be, say, RD. You can always think of RD. Which means that if you have different translates, okay, it doesn't work. Yes, do you have a pointer? Someone yesterday had a telescopic pointer, so it was very nice. I would not dare to operate with that big thing because I am afraid to break the screen. You have to be very well coordinating your movement.
Yeah.
Okay. So anyway, if there are two different translates of your base set, then their intersection should be empty if the translates are different.
So these are the smaller version.
Okay.
Not to break them.
Okay. Yeah. So, and then, so I introduced the sets, the packing, and then the result sounds this, that the upper density of lambda and this number symbol denotes that now we are counting So it's a counting measure thing that we are counting the number of points. Later there will be a more general motion. Okay, basically this is the uniform upper density, or in more full terms, asymptotic uniform upper density. We will in precise definitions later. So an appropriate density should be less or equal than 1 over the del Sart constant, the del Sart external value of h minus h. Okay? So this is the statement where d omega denotes the del Sart external constant on the set omega, and h minus h is just the element-wise difference of the two sets.
Are you going to define this d later?
Pardon?
The Sart constant, are you going to define it?
Yeah, I will actually, I will define and repeat these things several times so that you get more familiar or feel better, more comfortable with this abstract general setup. So don't be embarrassed that here at the formulation there are some foggy parts of this, but I wanted to tell you the goal or an archetypical result about which the whole study revolves. Okay? So, if h is centrally symmetric, then h minus h is the same as h plus h. So it contains 2h. If now 2h is interpreted by just multiplying by 2 these things, and if h in Rd is centrally symmetric and convex, then h minus h is 2h. Now I here have to underline that already we encounter here a situation where what we are saying makes no sense if we are not in Rd or not in a classical group, because what does it mean to be convex in a locally compactable group in general? Okay? It just doesn't make sense. Usually linear combinations cannot be interpreted in a group. It's not a field. Okay. So for centrally symmetric sense in general, the del Sart constant satisfies that dh minus h is at least larger or equal than d2h because of this inclusion. Looking for some external problem on a larger set gives a larger external value, or not smaller. And the same way, if we have a convex set, then dh minus h is just d2h, which is 2d d to the h in a d-dimensional case, so Rd. When talking about convexity, I restrict to Rd. So, in particular for the unit ball, the previous estimate can be written this way. And now I emphasize that now I'm talking about Rd, so this should be familiar. Whenever convexity is mentioned, then it means that we restrict to Rd. Okay? So the estimates of the above theorem can be sharp even in the general setting. Two major examples. When H is a tile, that it is not only packs but actually covers also, then this del Sart estimate is precise. And also there were cases of the ball packing business where this turned to be sharp. So this theorem above can be sharp.
It would be easier to follow the discussion if you define the del Sart constant.
I will. I just present some variations of the result so that you're familiar with the result, and then I will go to define in detail and explain all these things. So, we were talking about the strict packing, and this can be reformulated in this way. Why? Because, solve this equation, h plus lambda equals h plus h prime plus lambda prime. If only solutions which satisfy h equals h prime, and then consequently lambda equals lambda prime, so this solution, then that means that the h plus lambda are disjoint. Okay? If you have an intersection of h plus lambda and h plus lambda prime, it is an equation that h plus lambda, lowercase h plus lambda equals h prime plus lambda prime. If it can be solved only with lambda equals lambda prime, that means that different translates do not intersect. Okay, so it's a simple reformulation. And conversely, if there is a solution with h not equals h prime, consequently lambda not equals lambda prime, then that means that this intersection is non-zero, non-trivial. H minus h prime equals lambda prime minus lambda, and then therefore there is no intersection. So packing condition is equivalent to 3. And in that regard, the theorem can be formulated in a more general way. We actually can say this, that instead of assuming that we are talking about the base set H and writing here H minus H and H minus H everywhere, which is a difference set, we define H minus H as the pointwise difference. All differences H minus H prime. We can just put here any set, whether it's difference set or not. And still, I claim the same type of estimate. So it's a very general way to estimate densities, or conversely, you can estimate the delta constants by densities. So I mean, it's vice versa. So this is about the packing and the packing type conditions. So this small general result is really useful in other things. Maybe I don't go into details, but for instance, this unit distance avoiding sets, or the mutually unbiased basis, or a couple of other completely different things were already treated by this delta extremal problem in our book. I skipped this because I started a little late. Okay, so now I'm coming closer to defining the delta constant, but before that you have to consider function classes on which the external problem will be defined. So let me start with function classes. Simple notation, f plus f and f minus are the positive and negative parts of functions. So for any function and your locally compact abelian group, you can use this notation. Positive definiteness means this, I call this matrix type inequality, because this basically says that the matrix contained of elements fxn minus xn is positive definite in the matrix sense. Now, and the function classes. So one way to define a useful function class is to take all the continuous and integrable functions which are positive definite, normalized to have f0 equals 1, and with two prescribed sets. The conditions are that f plus lives in omega plus, f minus lives in omega minus. Okay, so this is the definition of a function class, of a subclass of positive definite functions, normalized and satisfying certain sign conditions on the function itself.
Sorry, are you sure that this L1 is okay? You don't need this integration of square?
I'm sure.
I'll ask another question. We assume your f is symmetric, but f of minus x is f of x?
No, I mean, it's a property of positive definite functions in general.
Because then 6 would be complex number.
Oh, sorry.
If f is not symmetric.
Sorry, I'm going in the wrong direction. Okay, so we are here. Okay. So what was your question?
If f is not symmetric, then left-hand side of 6 is a complex number. You're okay with that?
No. Okay. Actually, we consider real functions. Okay. So let us agree that we consider real functions. Whatever we do makes sense if we take complex functions, but if we take complex functions, then basically it turns out that the real part gives the same extreme value, and so it's easy to restrict to real. Does it answer your question if we consider every function real function?
6 will be still the complex variable. Okay. You can talk after the topic.
Okay. Yeah, okay. So because we are talking about positive and negative parts, it's better to restrict to real functions. Let us just neglect complex functions. Okay. So these are two function classes. My main point is, in this setup, that I use function classes only which can be well defined in locally compact abelian groups. So many authors introduce various variants of the Del-Sart extremal problem using function classes which satisfy certain decay conditions or smoothness conditions or both, or the same also on the Fourier transform, even Schwarz functions and such things. So in a locally compact abelian group, one should avoid these technicalities specific to the various classical groups. Okay, so even more function classes, let me cover what you encounter in the literature in RDC. So one approach to these type of Del-Sart type extremal problems is assuming that the function has compactly supported Fourier transform. This is usually termed band-limited functions. At least with the ball, this was studied by Gorbachev. Sorry. Kohn, Elkis, and Vyazovska impose decay conditions on the function itself and the Fourier transform side as well. This is very useful because assuming your function is automatically an L1, also you can work with it well. Now, okay, so here we study the following two extremal problems. So we have defined these classes, and the goal is to maximize the integral of the function that is the Fourier transform as A for both classes. But actually this is the same. This is the first theorem. We proved that these two extremal constants match. It has a lot of consequences. For instance, if we come back to RD, then it is not difficult to see that the Kohn, Elkis, Vyazovska class or approach give also the same. Okay. Now, specifications, what are the Turan and the Del-Sart extremal constants. Turan extremal constant is restricting to omega plus omega minus being the same set. So you assume that the function, both the positive and negative side, lives on omega. Okay? This is called Turan extremal problem in the literature, but actually goes back to Ziegel. And if we put omega minus equals G, the full set, that is no restriction on the negative part. So the only restriction is that the function can be positive only in omega plus, and otherwise it can be negative anywhere. Then it's the Delsart extremal problem. Okay? So this is the Delsart constant, what you asked, f at 0, or the integral of f, where f is continuous positive definite, f0 equals 1. And okay, the supports are, well, actually I should not write here compact. No, okay, I could write, okay, compactly supported. So this is the thing that now I can use the identity that C was equals C1, so I can assume whichever set of conditions on the function class. So this is one setup. Okay, so Gorbachev's approach is a bit different through the band-limited functions. So you can formally define this set G, W, Q. Here W is a subset of the group, and Q is the subset of the dual. So Q is the limit which limits the Fourier transform, so the band limit. Okay? And so the Delsart constant with respect to this class is again the same, but functions from this class. And one can consider then the limit case or the union of all compact supports. So you only suppose that the support is compact, whichever compact set, and it means that taking the union of these sets and in the external constant that the supremum of all these values. So Gorbachev's setup has some advantages. For instance, band-limited functions are actually entire functions of exponential type. And to work with them is somewhat much nicer. There is another advantage, not restricted to the ball. If you consider band-limited functions, then the existence of external function can be proved. Sometimes to analyze or to find the external function, the external value, therefore it's easier if you know for sure that there exists an external function. And in fact, this remains true even in general compact groups. Two young postdocs of mine did this research. But it's not clear how entire functions of exponential type can be used in local compact groups. Okay. So Gorbachev used this version of the Delsart constant. So the new restriction is that the support of the F compact. But he could prove that his Delsart constant, at least for the ball, is equal to the other way defined Delsart constant. But actually, we were in correspondence with him. This proof has never been published before, and he provided us the full proof, which is not that easy at all. I mean, it's not something like 7 pages in a paper which we published in a friendly agreement with him. So one has to prove these things. It's part of the experiment. Okay, so packing covering. So maybe I can be faster at this point. In general, packing is considered the setup when H packs with lambda, if this is satisfied. This is basically the same formulation, but more, how to say, loose, because you don't want to bother with the boundaries of your ties, and you say that you do it almost every. And the same way with covering, you don't bother with almost. The tiling means that you have simultaneously packing and covering everyone else. But if we have strict packing, so strict disjointness, then we will use the term strict packing. And I will explain why we stick to strict packing. Also, the ties will be called strict ties if the packing is not necessarily required. Okay, so so the strict packing condition was equivalent to this equality that we recall. And the generalized version of packing conditioning, strict packing condition was this. Where instead of a difference set an instant. So why to stick to strict packing? It is an example. So common sense has it that, okay, if you have a non-strict packing, then you just delete the measure zero subset of the packing set, and then you can pack with it in the strict sense. So what's the interest? And this is true, but we already saw that in the formulations of the theorems, there appears the difference set H minus H. And so let us consider an example. Let's prove the R and H is this set. Okay. Two additional points plus beautiful minus 1. So of course, in the almost everywhere sense, in the weak sense, it packs. Because if you take 2z and the translation are set, then basically it packs with minus 1, translates more or less cover R, and there are a few points, so almost everywhere. This is set, which is the intersection of the translates. And to get a strict packing, you of course throw away those two extra points. So modify the set by measures in your set. But what will happen for the difference? Well, for m minus n, there is no problem. It's minus 2, and we still have a packing type condition. This condition, this is still empty because minus 2 intersects 2z only in 0. And so, actually, there is a theorem that once you have a tiling and the delta are close to the 2 atoms, so she had this equals the measure of the tie. So you have the upper density 1/2 for the lambda set, of course 2z that's 1/2 by whatever you need the definition of the density. And the 2 random delta, of course, this one. So everything is perfect. What happens with the n? Then with the h. For the h, the difference set is already a lot larger because of the 2 extra points. And then one can see that this generalized packing type condition is not met. We have additional points. And that's not the main problem. The main problem is that now generalized packing with the translational set T is possible only if the density is less than 2/5. So strictly less than half. 2/5 can be done by 5z plus 2 plus 5z.
This needs to be true, I don't think it's true, so don't be embarrassed if you don't completely see why, but this is the fact. And then the tensor constant of Q is larger than 2. Actually, we constructed polynomials, geometric polynomials, showing that it's at least 2.2. So it's clear that everything that we are talking about is already changed.
But nothing that happened instead of points. 4 and minus 4 will get 1 and minus 1. Just like a close.
Yeah, so, okay, but still if you allow the boundary points, then
yeah.
Depends on directions, so in several dimensions.
4, right? 2 is not plus 3 minus 3. Second.
Similar, but maybe the calculation was somewhat easier. Okay, so anyway, this is just an example to show that from now on we are talking about strict factoring, and in the strict sense, because it makes a difference if we handle this almost less. Okay, so density. That's the key issue is this thing. Now we know what the tensor constant is. What are the densities? Actually, I had a hard time to look up the literature who introduced the notion of upper density, or I think the upper density. There are many names attached to it. Someone calls it Berlin density, others. Sure. Only the name of Jean-Pierre Cahn is not there. But to the best of my knowledge, after much research in the literature and asking people, I find that Cahn was the very first who introduced this. And very likely, everything occurred after him. Some of them probably knew already about Kahn's construction. Some of them rediscovering it independently. But it appeared in Kahn's PhD thesis, and the introduction is kind of marvelous. It will not be what you expect. The first construction of Kahn runs as follows. Consider uniformly discrete sequences. So there is a delta. We are talking about R now. So, okay, so under your line. So there is a delta that each members are delta separated, a uniform delta. So arrange the sequence in increasing order. So S can be written as a finite union of such uniformly discrete sequences if and only if this condition is satisfied, that in any interval there are constant terms. Of course, with any other interval. Now, Kahn says that if a sequence is just a bounded perturbation of an arithmetic progression, then he calls this a well-distributed sequence. It takes some thinking, but for instance, finite union of arithmetic progressions are still well-distributed, okay? So then what should be the density for that sequence? Obviously, you want that the density should be 1 over L. Now, if S is a subset of S prime, and S prime is well distributed, so it has a density 1 over L prime, then you want the density to satisfy the natural inequality. Smaller set, not bigger. So the definition is so simple. For any sequence, you just take the infimum of the densities of well-distributed sequences which contain yours. Have you ever heard this construction of definition? No. Yeah, because everyone uses the following definition. This is what we all know. It can be called asymptotic uniform upper density. Asymptotic because here we allow the size to grow, so only we are interested in the large scale. Uniform because here take for all R this supreme, so uniformly you want to estimate the thing. And so this is the form which occurred and reoccurred many times, and the first form kind of forgot. And Kahn proves that they are equivalent, so he gives this second form. D number was this one, and D star the previous one. So this is introduction to the density. Now, so we have two equivalent definitions. Also, a similar notion is used for sets like the unit distance avoiding problem. Then you have large sets which are not sequences but have positive Lebesgue measure everywhere. We want to talk about the densities. Then also in higher dimensional spaces. So for instance, the Lebesgue measure, the analogous definition is this. You now measure, not count the number of points which are in this inflated base set, but the Lebesgue measure of this, compared to the Lebesgue measure, of course. Yeah. By the way, here K can be a base set at your choice. So sometimes people use the cube, sometimes the ball is used, and in fact you can use any other thing. Landau actually proved by some hard epsilon calculus covering the boundary and so on that you can use any K. Yeah. Now, K. Let me just show you an application. The standard set of band-limited functions is denoted by B omega, which means that they are L2, and the support of the Fourier transform is in omega. And these are, of course, entire functions with order 1 and finite type. Can be represented as Fourier transform. And so these are two basic definitions that now follow. A set is called a set of interpolation if any f in B omega can be interpolated. I mean, if any initial data can be interpolated to get a function. So there is always a function which interpolates the data. And the set is a set of sampling if you conversely have now a function and you measure it at these sampling points, and the norm of the function in L2 can be estimated by the samplings. Okay, so the theorems that can be proved with these notions. One is due to Kahn. It says if the upper density is less than 1, then the set is a set of interpolation, and conversely, if the density is too large, then you cannot interpolate. And similarly, Berling proves that if the lower density, which is dual to the upper density, I don't define it, is large, then it is a set of sampling, and if it is small, then it is not. And Landau managed to generalize it to general sets in RD, at least part of it, the second part of it. You can see that Landau's theorems are equivalent to this second. As for the first statement, it's more complicated, so I don't go into it. Now, Landau's results can be generalized, and I have to mention this not only because it applies the notion in general LCA groups, but also because it was the first construction for uniform asymptotic upper densities which appear in print. So Gröheny, Kutniok, and Sipe constructed a different way, uniform upper density, I mean different from mine, and proved analogous results about sets of interpolation and sets of sampling. Okay, so it is a useful notion, this upper density notion. Now, okay, the Turan constant in packing, following, okay, going back to Siegel, there were attempts to estimate packing densities by the Turan extremal constant. It is a later refinement that one can also use the Delsart constant. I will be brief because I'm running out of time. So anyway, but you can see that there was some literature about that, and finally I managed to extend this to locally compact Abelian groups by this density. And the key issue was already there, is that how to deal with the density notion. Okay, so the Turan constant is less or equal than the Delsart constant, because in the Delsart constant the function class is wider. You allow it to be non-zero, to be negative, maybe outside of your set. There are examples there. It is really shown that they are different. So in packing, it became a standard to use the Delsart bound or the Herky bound. And it goes back in certain contexts to Delsart. Okay, trigonometric polynomial or the torus set up to Udin and Levenstein. And so this is the well-known Delsart bound for the packing density. Which is sometimes exact. So the difference between the Delsart and Turan, that we don't assume the whole function to be supported in omega, only its positive part. And then here is the result. Let me just recall it again. So here there appears this density. So I would like to explain our construction of the density definition. How much time I may have?
15 minutes.
15 minutes. Okay. So one has to recall a couple of basic facts about locally compact Abelian groups. So locally compact Abelian group is a group equipped with a topology, an Abelian group equipped with a topology with which it is locally compact. So I use this complexus or Minkowski sum notation and Niemann multiplication. I denote the algebraically generated subgroup by this bracket. Characters of continuous homomorphism to the unit circle, and the set of all characters equipped with the local uniform convergence topology for the dual group. Okay, so I don't go too much into detail. It's known that the second dual of the locally compact Abelian group is the original group. It was mentioned here that, of course, for finite Abelian groups, the group and its dual are already isomorphic, but not in general locally compact Abelian groups. So one has to be very careful what lives in the group and what lives in the dual. The main issue that there exists translation invariant Haar measure. And with that Haar measure, you can, of course, define a lot of things like the Fourier transform or convolution, even convolution of measures. And you have Blancherel type identities. And you can define positive definite functions by the same positive definiteness of n by n matrices formed by elements xm minus xm. So it's no problem. And you can characterize the positive definite functions by the Bochner's theorem the same way as it's known in classical. Any positive definite continuous function is just the inverse Fourier transform of a non-negative major living under the dual group. Now, closer to the heuristics, how we wanted to construct the notion of uniform acyclic upper density. So what is the problem? That we don't have dilates. In RD, we just started out from a base set, say K, and then we decided to inflate it, to make the density sensitive only on the large scale things. And this is a main problem because we don't have dilates. Also, we don't have a standard neighborhood. So, I mean, of course, also in RD, I explained that whether it's the square or the disk in R2, say, it gives the same thing. But in a locally compact neighboring group, it may happen that different neighborhoods generate different subgroups. So there are differences between the local neighborhoods. How to ensure that using some inflation, which we don't have, but okay, somehow we find some substitute for inflation, exhausts the whole group so that we will really measure everything and everywhere. So the first problem is to do something about dilates, which don't exist. And then we encounter the following nice lemma, which is a basic lemma in the theory of local compact neighboring groups. And this says the following: for given epsilon and the compact set C, there is always a Borel measurable set V, such that the Haar measure of V plus C is only a little larger than the Haar measure of the original set. I mean, compared to, I mean, the measure can be huge, but only epsilon times. Okay? So this is a basic lemma, which is explained in Rudin, in Hewitt-Ross. And so this gave a hint how you can grasp that the set is large, because how you can interpret this thing. Consider RD and consider that V is some relatively nice set, like a ball. Okay? So then what is V plus C? V plus C is a bounded perturbation of the boundary. I mean, V and a bounded neighborhood. So if C is, say, okay, it's a compact set, so we should think of it as a small set, like the unit ball, and V is a ball of radius R, so an inflated big set. Then the difference is not much. V plus C is the ball with radius R plus 1. Okay, so this is the meaning of it, and that allows us to consider, instead of Rk, then R tends to infinity, instead of Rk, just to take here V plus C. Why V plus C? Because if V is indeed large, in the sense of the previous lemma, then it's almost all the same if you put here V or V plus C. And if V is not large enough, then it means that V plus C could be much larger. than V here. So from the original thing, this additional inclusion of C decreases the ratio. And since here you are looking for supremum, it will drop out from consideration. Okay? So this way we can grasp the need that this V should be large. Okay? So, okay, so then we take supremum with respect to measurable sets which compact set. But then actually we can drop also the supremum with respect to translation, because if we consider all sets, then all of its translates are already in the consideration. And of course, we want this thing really to grow, so we want to ensure that larger and larger compact sets are taken, and in the limit, even this C is large. So, so we take infimum. It takes a while to digest this, so, but I try to explain. Okay, so before giving the definition, let me just bring under one umbrella sequences and Lebesgue or R measurable sets, and even measures in general. So for the sequence, already Kahan associates the counting measure. So if it is just, so it is just a measure. And the discreteness means that this measure has only finitely many points, so has bounded total variation in any translates of a given compact neighborhood. Okay? So the right family of measures here should be measures which are locally uniformly bounded. Not necessarily of total variation, like the Haar measure is not of finite total variation, but everywhere its mass is bounded. Okay? So for these measures, this class of measures, we would like to introduce a good definition of uniform asymptotic upper density, and here it is. We take this. We measure, according to our measure, the sets, and divide by the Haar measure of C plus V, take supremum over V, and then infimum over C. So even after so much explanation, of course, it's not absolutely clear that this is a correct definition. But anyway, it's clear that for sets, you can consider the trace of the Haar measure in the definition, and then here there appears this trace. And for sequences, you can come back to this point counting measure. So it covers the previous cases. And so the first theorem one has to prove is that if you come back to RD, pick a base set, normalize its origin to be 1, then in RD, this corresponding classical notion of the respective upper density equals to the one in RD according to our new definition. Okay, so it is indeed a generalization of the classical notion. And there is already a nice corollary, a windfall result. It proves without any epsilon calculus and the bothersome work of Landau that for all k, the definition in RD are equivalent. Because all are equal to the local compact Abelian construction. Okay? And there is a warning message also. Things are not always completely trivial. For instance, if k is not bounded, then our construction blows up. There are such kind of funny things here that sometimes you would think that in some situation that could be even the better, and it's not. So, okay. There are favorable properties of these densities. I don't list all of them. I mean, don't read all of them. One thing I only point out, that of course, since in the supremum infimum, you take supremum for all sets, so even for translates, and in the denominator, that is the Haar measure, it's a translation invariant. That's the most basic thing we expect. Okay, so one can work with this notion. But it's also true that, with equivalent reformulations, sometimes some properties are easier to see. We are still working on that with Imre Ruzsa. We know up to now something like 8 different equivalent definitions, and it's quite nice interplay between the various things. I did not explain how. Okay. So if I have time for that, I would like to analyze this 1 plus epsilon lemma, giving the key. 5 minutes. Okay, maybe I will do it. So, recall what the lemma said. It was the statement. And Rudin makes 2 remarks, one being that one can get this with an open set V, but his proof does not give it. Hewitt and Ross proves it with an open set. And both proofs rely on the structure theorem of locally compact abelian groups, and even Rudin directly points out that the presented proof is depending on it, and using it. So in the theory of locally compact abelian groups, it is kind of, in number theory they say that if you use complex analysis, then it is analytic number theory, otherwise it's elementary. It could be more complicated, but there is a big division between the two things. So things are considered more elementary if you don't use complex analysis. Now this is the same division limit that if you use the structure theorem, then it is more complicated. But let us give a new proof found by Imre Ruzsa, which will really give you the right nature of this lemma. So let K be an open neighborhood of C, still with compact closure, so that its measure is not much larger than C. C was a compact set that is given at the outset, so we want K to be open, because of inner regularity of the Haar measure, you can always, or outer regularity. So the measure of C can be arbitrarily approximated by an outer open set. Okay, so fix any element A of K and consider this covering. K closure, which is then a compact set plus K closure, is of course contained in this set. Every point is contained in this. To translate by A is needed only because we don't know if 0 is in K, but if T is here, that means that it is trivial that this is contained. Okay, let's go. Sorry. So the point is that it is an open covering. There is a finite subcover. So take the T's which define the finite subcover. So that means that K plus K is contained in this set. Define Vm to be m times K. So m-fold addition. So then by induction, Vm plus 1 is, okay, so K plus K is in K plus T, and so you apply it n times, and you get this. It means that K plus m times T, the T set. But by commutativity, the number of elements of MT can be estimated. It's choosing among n elements m times. So it's this m plus n minus 1, choose n minus 1, which is just polynomial. So the measure of Vm is less than m to n minus time, m to n minus 1 times the measure of K. K is here, and here is the number of translates. We have that many translates. There is a shift of indices here, so m plus 1, so therefore I can write it. So, there must exist some index m where we have this inequality, because otherwise we would have always this, which gives an exponential growth. And the growth order is just polynomial. Okay? So it cannot be valid for all indices. Just pick. You know, C was part of K, and K plus Vm is Vm plus 1. So just pick V equals Vm, and you get an open set with the required properties. It satisfies this inequality. So needed no structure theorem, needed only commutativity that have been, because otherwise the choice from T would result in many more different elements. But actually, it finished the proof by these elementary considerations. So it's short and direct, it's the open set version with these, and absolutely free of any structure theorems. Okay, so maybe I just mention that this also reveals that there is a big room for generalizing the notion, because you can get away by sub-exponential growth of the MT. So if in a group you know something like, say, Lie groups or nilpotent groups, then there is chance that you can extend the notion of this density. And these lattices things I don't go into detail. I also tell what the structure theorem is, just to make it. And I want to say a few words about the proof of the main result. It will not be a proof, just a very short sketch if I may. Okay, so basically I focus on two special cases. So we need to prove first, and it is really needed in the proof, a very special case where we assume that the set H is not only a packing, but it ties G. And the translational set of the packing or tiling is a finitely generated lattice. So this special case is proved first. And then we remark that when lambda is discrete, for compact G it must be finite. So the compact case can be that without the notion of density because you have finitely many translates, and the density is obvious that it is just the number of lambda because you normalize the R measure. And then the proof is basically a tricky combination of double sums. We need double sums here. I don't describe the proof in detail, but it is like 1 page. And so the main proof is kind of simulating the compact case using this slow growth of the sets Vn. Where now the Vn are defined this way. This is kind of equivalent to the construction we had before. And we need that our constructed Vn's admit a time in the certain set. Okay. And third, there is a lemma which says the following, that our abstractly defined density admits the following nice property. For any epsilon and any set V, there is a translation Z, so that the translated copy of this V admits rho minus epsilon measure. This is important in devising equivalent definitions, so I worked out here how Kahn's definition can be repeated in the local compatible group setting. It's a bit long. In particular, you need to tell what the density of the lattice is, and that already requires some considerations. And here is a definition what Ruja proposed, and this is again different looking from my previous construction, but also kind of natural, even if surprising that it works. You can define this uniform asymptotic density by this simple formula, which is kind of surprising because here you consider all V with positive measure. So it seems suspicious that also small sets can be very good. But the point is that you take your infimum, and this tends to average out things, and so closer to the infimum if V is large. So, thank you very much, and excuse me for
Thank you. I guess we have more time for questions or discussions, but perhaps we have coffee break.
For discussion.
Sorry?
Full account for discussions, questions.
Okay, okay.
Coffee break.
By Peter Grabner, you see the title, please.
So, thank you very much. We first thank the organizers for inviting me to come here. This is joint work with Austin Anderson, Maria Dosta, Ryan Matzke, who is here, and Tanya Stepaniou. Yes, it's nice to have this ambiguity. Green energy could be green or green. Okay, so I will mainly talk about discrete energies. You possibly have heard about this notion quite a bit during this meeting. So in general, you have a manifold M and a bivariate kernel which lives on M cross N, but without the diagonal. Usually there is a singularity on the diagonal, so if you insert the same point twice, then this is not defined. And the associated energy is just the double sum of all possible pairs of points and avoiding the diagonal. This has been studied very intensively. This is motivated from the classical continuous analog potential theory. This is a famous book by Hardin, Volodachov, Hardin and Seff, very recent, that collects all the known facts about these notions of energies. And there are natural choices for these kernels, especially if the manifold shows some symmetry. So there's one, this is the green kernel, the green function.
It doesn't work. It does not work. So the pointer is not.
Okay, yeah.
That's why you need a stick. Okay? So this is a problem we all have
Okay,
to
let's.
deal with, I'm afraid. So
Do you need a stick?
No, they. You have one?
I was again going to borrow one. From
Okay, so anyway, so actually the green function is a very natural choice because it comes from the Laplacian and it actually encodes all the curvature issues that one could possibly have. And the Riesz potentials written in the way I've done it here more or less assume that M is embedded in Euclidean space. Actually, this is something that we won't have in the cases that I'm discussing, but we will have a notion of green energy, of Riesz energy. So for a given kernel and a fixed number of points, we want to have information about the minimal energy associated to the kernel and the number of points on the manifold. So we take all n point subsets of M and try to get the minimum that this energy takes. And there's some general knowledge on this. So there is a constant which is actually given by the continuous analog of the problem, constant times n squared, plus a lower order term. This is a very general fact about these energies. Of course, one needs some assumptions on the kernel. Something like positive definiteness would be required to take that. And then this energy is well defined, and one can discuss the properties of the minimizing measure. And then also as a general fact, if one then takes the empirical measures associated to the minimal energy configuration and let n tend to infinity, then these measures tend to the minimize of the continuous energy problem. So these are the rather general facts, and then if we look at the special case of the green function, then we have this green energy, and in this case it has been proved by Beltrán, Corral and Criado del Rey that the minimizing measures actually are given by the uniform measure on M. So this is what I was alluding to before, that the green energy is more or less a very natural choice because it has the preferred measure on M as the minimizer for the energy problem.
So you consider compact manifolds as well?
Compact, yeah. Okay. I'm only talking about compact manifolds. Sorry, I should have pointed that out in the very beginning. Otherwise, everything could escape to infinity, and then there is no point in studying that. Then one would have to add a potential that would confine the points to some finite subset. So for other kernels, the minimizing measure is usually not really a nice or natural measure, and this is the reason why we were looking for settings where the minimizing measure is more or less automatically a very simple and nice measure, and this is symmetry. So if the space allows for enough symmetry, then one could obtain some uniform measure on the space, and of course the uniform measure would then be the measure inherited from the symmetry group acting on the space. So, and there's also a good reason for looking at two-point homogeneous spaces, because these are especially nice, and everything we can talk about is actually a function of distance, which makes things much easier. And so, just to point out, a space is called two-point homogeneous if for any two pairs of points that have the same distances, there's a group once again, there's a space, there's a Lie group acting on the space, and for any two pairs of points with the same distance, there's a group element that transports the 2 points to each other. And there is a characterization of these spaces. Once again, we only are interested in the compact spaces, so the compact spaces that have this property are the d-dimensional sphere and the projective spaces over the reals, the complex, the Hamiltonian quaternions, and then there's one exceptional space that is the two-dimensional projective space over the octonions. And this does only work for 2 dimensions over the octonions because they are not associative. And we are especially interested in those 4 spaces because the sphere has been dealt with in many, many papers, and more or less everything is known about the sphere.
And excuse me, you consider manifolds in Kerr spaces?
We are restricting the manifolds now to those 4 types of spaces.
And last, this is Kerr space.
Yes.
And how do you define manifold in Kerr space? This is.
So that inherits the structure from the construction.
But this manifold, this space probably even known as associative.
Yes, the octonions are non-associative, but this part of the structure is not actually needed. We only look at it as a space, as a real manifold. And actually, it turns out that all these spaces can be more or less studied by the same machinery, by just choosing different parameters. I will come to that in a second. Okay, this is so I usually write Fp to about d-1 for these spaces, F being reals, complex, Hamiltonians, octonians. And of course the dimension over R of these spaces is 1 for the reals, 2 for the complex, and so on. And there are those 2 parameters, alpha and beta, that make frequent occurrences because they are the parameters for the Jacobi polynomials that will occur at some occasions. And we use theta to be the geodesic distance, and we actually normalize this geodesic distance to take values between 0 and pi over 2, which is just suitable normalization. And for instance, one can write the heat kernel. Then you see these are the eigenvalues of the Laplacian, and this is a normalization. And it turns out that all the functions are more the Jacobi polynomials are usually evaluated at 2 times this geodesic distances. Just turns out to be the correct normalization. And of course, this factor here is nothing else than the sum or the projection kernel that projects to the eigenfunctions of the Laplacian for the corresponding eigenvalue. This is something that we will need later on. And the green function, or the green kernel, is then, or can then, we will use it later on, can then be expressed in terms of the heat kernel. And of course, this is again a function of distance. And after some computation, one can actually get rid of the Jacobi polynomial and replace them by powers of the cosine, which still doesn't say much about this function, but it turns out that, of course it turns out that this is something that can be expressed in terms of a hypergeometric function. And so actually this is, because of this n here, this is the primitive of a hypergeometric function. And it turns out that this is still an elementary function, at least for the values of alpha and beta. And I just displayed that for curiosity, more or less, because it seemed to us that this was not available in the literature. You see, these are powers of sine, logarithm of sine, and here, for those different cases of alpha, in the other case, here we have also theta occur. So there's an elementary expression for this function, say elementary, but still not too nice looking. And for the Riesz kernel, there would be 2 obvious choices, namely just the power of the geodesic distance, or something that would come from an analog in the case in comparison with the sphere, where one has a chordal distance, and the chordal distance would then be taking the sine of the geodesic distance, and it makes more okay, possibly not more sense, but it's more easy to be studied if one takes the sine of the geodesic distance as the basis of the Riesz kernel. And usually this the energy integral is only convergent if this Riesz parameter is varying between 0 and the dimension of the space. And if one just looks at the setting, one could expect an asymptotic behavior of the same kind. So there is this constant coming from the energy of the normalized surface measure, and the big O term, or the next order term, should be of this order. And actually our goal was to prove that and to actually show that this is the right order of magnitude of this term here. Actually, one could be a little bit more precise by writing a negative sign here, because this term here, this next order term, is actually negative and bounded between 2 constants times this power of n. Yeah, this is, so there is a constant. So this is a conjecture that was also popularized in papers of Ed and his co-authors, that the there's this main order term, and the second order term is exactly of this order of magnitude with a constant, and then there's a next order term of this form. And actually this conjecture has only been proved for the sphere of dimension 2. No, not even then. So for the sphere of dimension 2 and s equals 1, I think. So for a very restricted setting. The Coulomb case, yeah. And for all other values of s and all other possible settings here, this is not known. And it is also conjectured that this constant here encodes the local structure of the minimizing configuration. So on the sphere of dimension 2, one expects that a structure that locally looks like the hexagonal grid, or mostly looks like the hexagonal grid, would give the minimizing configuration.
Do you deal with s equals 0 like the analog of the log?
Yes,
As well?
this is also included in the paper, but I didn't want to go into that because it's always an extra exceptional case. So there's also a logarithmic energy that is usually associated to s equals 0, and then this term becomes an n log n.
Right.
Okay. Okay, and what we achieved was to give upper and lower bounds for these energies, and that shows that the second asymptotic term, at least, or the second order term has the correct order of magnitude. Of course, this does not prove that there is a second asymptotic term. So for the Rees energy, there is a bunch of, there's a machinery present. There's especially a method that Johann Brauch had used for getting lower bounds for the Rees energy on the sphere SD. And this is actually an extension of ideas that were used in the very early papers on Rees energy on the sphere, namely you compare the Rees energy or the distance function that is used for the Rees energy with the continuous version, so you just translate it a little bit by delta, and Johann Brauch's idea consisted in applying Taylor's formula to this and to more or less smoothing this function here in the correct way, and then playing with delta that would give the correct order of magnitude of the error term. And this gives a lower bound of this form for the Rees energy. And the main difficulty is that as opposed to the difficulty, as opposed to the case of the sphere, where everything is expressed in terms of Gegenbauer polynomials. In this case, the Jacobi polynomials do the trick, and there are less obvious relations between them, or you have to look in different places to find the corresponding identities. For the green energy, I should point out that the green energy somehow, because the green function is more or less like the Rees energy, except that there are many more terms of that kind, and there are a little bit of perturbations here, but the green energy in principle is like a Rees energy, but only in principle. So we adapted a method that is is hidden quite a bit in a book where you would not expect that. There's Lang's book on Arakelov theory, and in the appendix, and that was again pointed out by Ed to Dami and Carlos, that in the appendix there is a lemma that is due to Elkies, and that does the trick. And this is based on the fact that the green kernel and the heat kernel are related in this way. And the heat kernel has two nice or important and nice properties. At first, it is a positive definite function, and secondly, it is positive. And the positivity of the heat kernel then can be used to get lower bounds for the green function in terms of the heat kernel, and try to popularize that idea. So we set this green kernel with index t to be the integral over the heat kernel, and then, as I said, because of the positivity here, one can easily derive this inequality that should be, no, it's t, okay.
And please, what about Arakelov's theory for instance, quaternionic or octonionic Cayley spaces? Arakelov's theory only for complex numbers.
No, actually, in this book here, this is a lemma that gives this lower estimate, and we only use this lemma. This has actually nothing to do with Arakelov theory. I pointed that out, that this is somehow this idea was hidden in some literature that is actually totally unrelated to the. And we get this inequality here, which is nothing else than just exploiting positivity of the heat kernel and letting this T naught tend to 0, which would then give the green kernel or the green function gives a lower estimate for the green function in terms of this function here. And the nice thing is that this function actually has an explicit expansion in Jacobi polynomials, and this is not only explicit but uniformly convergent. And so one can work with that. The green function also has a Fourier expansion or Laplace expansion in terms of Jacobi polynomials, but this is convergence of this series is more or less very, very delicate. And this is what I already said. And this gives a lower bound, which is exactly of the order of magnitude that one would expect. And even the constant is explicit that one could get out of that. So this summing up more or less says that for the Riesz kernel and for the green kernel, we have a lower bound of the correct order of magnitude. For the green function, you see that this n squared times the integral is not there because the green function has integral 0. So there is no main order term for the green energy. Okay, for the upper bound, one simple idea that is very present also in this context would be to integrate over all possible point configurations, and the first and simplest point process one could take for that would be to take IID points, which more or less immediately give you this upper bound. So this n squared minus n is just the number of terms in the sum, but you see the error term, the order of the error term is the wrong order. Too weak, and it has become more and more popular in this context to look at determinantal point processes, which are very are very nice because on the one hand the points are no more independent, but the quantities we need can still be computed in a rather nice way, and determinantal point processes have a built-in repulsion between different points, which is exactly what we expect from minimal energy configuration. So since there is a blow-up of the energy if points come too close, we would like to favor point configurations where the points obey some distance. And there is a So what we also want to have is that the process that we define obeys the rotation invariance of the spaces. So we look for rotation invariant subspaces of L2 and then take the corresponding projection operator to define the determinantal point process. And if we have that, and this, if we take a orthonormal basis of this subspace V, which is denoted by these functions psi, then this is the projection kernel for this space, and more or less we only would have to find the rotation invariant subspaces of L2, which is more or less very basic representation theory of the groups acting on these spaces. And actually it turns out that for every eigenvalue of the Laplacian there is a finite dimensional subspace associated to the eigenvalue, and if we take direct sums of these spaces, these are all examples for finite dimensional rotation invariant subspaces of this L2. And if we take these eigenvalues in increasing order, starting with the smallest one, this is a space that has especially nice properties, and we call the underlying or the resulting determinantal point processes the harmonic ensemble. This is very similar to what Cordy and his co-authors did for the sphere. And if you take this, then the projection kernel can be expressed in terms of Jacobi polynomials, and everything works very well for the computations that have to be done. So just to show you what the quantities are that have to be computed. So the projection kernel actually can be expressed in terms of the Jacobi polynomial, but the one index is going up by 1 because of the summation. And if one wants to compute the Riesz energies, or the expectation of the Riesz energies, one ends up with an integral of this form here, which is a Jacobi polynomial squared here, but you see the Jacobi parameters don't fit. So this is alpha plus 1, and here we have alpha minus s over 2. This minus s over 2 comes from the fact that we are integrating against the energy, which would just be 1 minus x to the negative power s over 2. And actually such integrals occur more or less everywhere in this context. So here you integrate the square of an orthogonal polynomial, but you more or less change the weight, so you integrate it against the wrong weight. If it would be the correct weight, then this would just be a quantity that you look up in any book on orthogonal polynomials. If you change the weight, then of course this is something different. And so this was the motivation for a paper that I wrote together with Johann Braucher. We developed techniques for the asymptotic analysis of such integrals. There are more or less two possibilities. One would be to use these connection formulas, so these Clebsch-Gordon coefficients, the Jacobi polynomials express these polynomials in terms of polynomials which have the correct parameters, and then you would end up with sums. Actually, these sums turn out to be holonomic in the sense of this Wilf-Seilberger theory, and so actually many of these sums that occur in this context can be used by can be treated by using Seilberger's algorithm, and from this one could get at least an asymptotic equivalent for that. The other possibility would be to replace the Jacobi polynomials by the classical Hilbert approximation and treat this integral by, say, very classical asymptotic analysis. And then there would be two steps. The first one would be to replace the Jacobi polynomial by Bessel function and then insert the asymptotics of the Bessel function and cut off the integral and all these usual steps that one has to do in this context. So in any case, we could produce upper bounds of the desired form. The constant, of course, is more or less explicit, coming from putting together all the intermediate steps of these different asymptotic analysis. And you see this fits with the lower bound that I have presented before.
It is asymptotic, but do you have some non-asymptotic bound? Can you be substituted by general bound in this one? Because it is asymptotic, right?
Yes.
Asymptotic bound. Do you have something like for that works for all n?
No, this works for all n. Yes.
All n.
Yes.
Okay.
Okay, so sorry, not quite. So if we use this determinantal process to produce the points, then this upper bound here only works for the dimension, for n being the dimension of one of those spaces that we use for defining the determinantal point processes. So actually n is running only through a subsequence of the integers for this. But there's a second possibility, which is actually also a determinantal point process. You use jittered sampling, so you partition the space in equally sized pieces, and this can be done by a result of Gigante and Leopardi. So you need that. You can partition the space in equally sized pieces, and you still have control on the diameter of the pieces. And this can be done, and then using this construction, one gets a similar upper bound of the same order, but the constant is no more explicit because the construction of the partition is not explicit. And you only know that you have control on the size of the pieces, and you have control on the diameter, but you do not have control, or the constant that controls the diameter is not explicit. And so this upper estimate is true for any value of n. The construction using determinantal point processes gives an explicit value for the constant here. And so there's an explicit value for the lower bound coming from this other method, and there's an explicit value for the constant on the upper bound. But there's still a gap in between, and as I pointed out before, the conjecture would be that there is an asymptotic formula with this term here being the second order term, and then there would be a next order term, error term. Yeah, so some concluding remarks. As I pointed out in the beginning, the restriction to two-point homogeneous spaces mainly comes from the fact that everything is still univariate in a sense. So as soon as it comes to the computation of the quantities, you only have one parameter, namely the distance. And then you have these Jacobi polynomials, they are evaluated at this distance, and everything becomes simple for Of course, then one could go one step further and look for homogeneous spaces, and among these more general homogeneous spaces there's one more or less exceptional, namely SO3. In this case, it turns out that everything still can be studied using only one parameter, namely the rotation angle, and this was done by Carlos Beltran and Damir Ferezovic. They more or less performed this whole program of estimating the energies on this space from above and below, and still, as I pointed out, everything is univariate in the computations. Of course, the next step would be to go further for higher dimensional rotation groups, possibly more general Lie groups, Grassmannians, but there the harmonic analysis would then be definitely multivariate. You would have to use multivariate asymptotics to be able to compute all the parameters that we have computed. So there is one further step of complication. We have started a bit to think about how to do that, but possibly we are only still at some early steps of this program. And this is all I wanted to tell you. Thank you for your attention.
Perhaps we have some time for questions or discussion, because this is just the last talk before the break.
Okay. What about the finite two-point homogeneous space? Actually, let us consider finite two-point, say, Hamming space or space, right? Actually, you have all ingredients here, right? It works for finite space. It's also. Do you have idea? Can you apply this technique?
I've not thought about that, to be honest.
They also like Hamming space, conjugate polynomials, or Johnson space. What? Do you have this chapter?
Some energy results we have,
yeah. Yeah, energy. Yeah, the problem is, of course, what I mentioned. Problem is your all this inequality asymptotic, right? To find space, you have to, I don't know how to fix it.
You trace the space.
But however, you said that it can be also, you can also give inequalities non-asymptotic for all pair. Maybe you can.
Yeah, but so if I understand that correctly, you would more or less have to find inequalities that take the number of points in the space as the parameter, and then let the space. This is what you said. Let the space grow in that respect. Because if you have a finite space, a fixed finite space, then you don't have to have the chance to play with the number of points.
Okay, suppose the dimension is very high for Hamming space, right? You have n. We can actually also write some inequalities.
Okay. Yeah, as I said, so we have not thought about that, but this is something that would fit into that into that program as a next step, or possibly as a step.
Yeah. So because Grassmannian actually is exotic, right?
Yeah.
So we try a lot of attempts to extend this theory for Grassmannians, but finite space is very interesting.
Yeah.
It also makes sense.
I also want to just toss out something. So the upper bound that works for all n is to be able to have it work for all n. That's coming from doing fitted sampling, so you need an equal area partition. Once you're in a finite space, like the Hamming cube, you can't do that unless you're partitioning into some power of n number of pieces. So you'd have to do some kind of adjustment to account for that.
Yeah.
And that would get a little weird.
And also for Hamming, I'm not sure that there exist grid function because it is a theory. I'm not sure. So for finite, it has to be infinite, right? To have a grid function, discrete version.
Yeah, you can have discrete versions because there is a discrete Laplacian, and then you.
No, for infinite, it does exist. For grids, I know that there exists theory for grid function, but for finite, probably not. It was the constant. Maybe I'm wrong.
I think so because you can see this as a graph with transitions, and then you have a Laplacian defined by the transitions, and then you have a green function. And that was you have something like a green function.
For grids, they exist. I know.
Excuse me. Thank you for a very interesting talk. Please, do you consider algebraic varieties over quaternionic or over octanionic or Kelly spaces? Algebraic varieties.
I understand. We have not done that. So one of the points is here. Here, so for the green energy, this is very general fact on any manifold, on any compact manifold, that the minimize of the green energy tends to some nice measure. If you do the same on a general manifold, and you use the Riesz energies to minimize, then the minimizing measure that you get exists, but in general has nothing to do with the surface measure. So this would be some exotic measure, and then all the results would be about comparing the distribution you get with this exotic measure. And of course, if you do this for algebraic varieties, even over the reals, then you have an ambient space that would help for, say, for instance, defining the Riesz energy, but you still end up with some measure that only comes up as a solution of this potential theoretic question, but does not really have a nice geometric meaning. Actually, there are some steps in that direction. So, for instance, this is something I did not talk about, but something that fits into the general theme of the conference. There are point configurations that are especially interesting, namely spherical or designs. So this would be point configurations that, if you insert them in here and you take, for instance, in the case that I'm discussing, you take Jacobi polynomials, these sums would actually be 0 for them, and 0 is the correct integral. And there was this result of Bondarenko, Radchenko, and Vyazovska some 8 years ago, I think, that such designs exist and they have in the correct order of magnitude for the number of points.
No, it's square.
What?
Square the number on the sphere.
Yeah, but the correct number of points, what you expect more or less.
Yeah, it's the square of the number.
Yeah, this result was extended to algebraic varieties, for instance. So compact algebraic varieties, you can choose points on them.
Not complex. I am asking about quaternionic and octanionic O'Kelly spaces.
Yeah.
About this. For complex, I understand.
Yeah.
But for more general.
More general. So this is something we did not look into. It was just to show that something has been done in that direction.
Well, we still have time.
Sorry?
We have time. For question. Yes. No, it's well, I was wondering about these constants that appear here. Well, in the case of the sphere, there are these conjectures about the actual value of this in some dimensions, privileged dimensions where there are some nice lattices and things. So there's something of this kind to be expected. So there's any conjecture for the value of
I think
the optimal value. If there was an optimal value.
So I think the same, more or less the same conjecture.
So it will be the same as the
holds because wait, just give me a second. Here.
Yeah.
So we use that same notation, right? So is it the same constant? So we use that on the sphere, right? For S.
So possibly not the same constant, but they should be connected in the sense that your conjecture says that these constants come from a specific configuration which locally has a lattice structure. And the same happens here because we are on a homogeneous manifold.
When there is a good lattice, we don't know.
Yes.
So this green, for example, is supposed to be this universal minimization theorem by Kumar, and so it's supposed to require something from the kernel. No? So I don't know if the green function is positive. So there's some requirement for the potential knowledge for this generalization to
yeah.
So I don't know if it's already in the hypothesis, so no. So it's totally positive. I mean, the
green kernel is of course conditionally positive definite.
Yeah, but this thing that it changes signs, derivative is changing signs. This is called total positive.
You mean the?
You mean completely monotone?
Yeah, completely
monotone.
Yeah. But so if it was if it's completely monotone, then it fall on the hypothesis of this Kumar.
Minimizers.
But the big question is whether this constant would actually come from these lattice-like configurations, and whether there is a
first question is whether the constant exists.
Exactly.
So that first prove that the constant exists.
No, but if it exists.
I have one more question. What about Tori? What about torus? Because it is a very natural, came from applications, because when you have a periodic. Yeah. Do you have any? I remember that maybe you know, he told me that he also considered some energy, right? Do you know this paper?
Usually a lot on energy, right?
It's an application.
You have papers about these periodized energies.
Yeah.
So it's very natural, and I know
So
some
periodic cases, yeah.
periodic.
But
for physics.
But that would be, I think, the analog, because you want to avoid artifacts coming from curvature. So if you embed the torus in R3, then you have a measure that is supported only on the outside.
I was talking about the periodic.
Yeah, in the periodic you avoid curvature. You have flat tori.
Yeah, flat tori. Yeah.
Flat. You don't have any boundary.
Not necessarily like
Yeah.
in this case.
Yeah, but you would like to avoid boundaries anyway.
If there are no further questions, let us talk the speakers in this morning session before closing it.
Is Damir Chirizovic. So please, the floor is yours.
Thank you very much. So I'd like to thank the organizers. Thank you for having me here. I'm very happy to be here and talk about my research. So if you have read my abstract, I promised basically to give you a sequence of a point sequence on the unit 2 sphere in dimension 2, such that the inertial segments will be uniformly distributed. So in order to just give you a first notations, let's perhaps introduce what it means to be well distributed in the sphere. So a spherical cap is usually, again, it's cut basically by having a piece of the sphere off, then you have an intersection, and this intersection will be the boundary of a spherical cap. So note either the interior or the exterior could be a spherical cap. We don't know it from this picture, we just know that the boundary is basically the red line. Now, finally, point sets on the 2 sphere, or basically any sphere, what you can consider is the LP discrepancy, and that's defined in the following way. So you take your spherical cap with center W and height T. You count how many points fall into the spherical cap, and you compare with n times the normalized surface measure of the spherical cap. Now you take the absolute value of this expression, take the power p, and you integrate now over the 2 sphere and the interval -1, 1, which gives you the height of the caps. So sigma is the uniform probability measure on the sphere, and et usual Lebesgue measure on -1, 1. And in the end, you again normalize by 1/n to the p, and if you take the pth root on the right-hand side, you will get the LP discrepancy. So intuitively speaking, if the ratio of points that falls into the cap and lies outside the cap is always comparable basically to its area, then this expression will be small, and in the end you will have a smaller value on the right-hand side, indicating that the points will be nicely distributed in the sphere. So this is for integrals. What you also can do is replace the integrals by the supremum, just like this, and then we talk about the spherical cap discrepancy, a notion which is much stronger. So again, you compare the points in a spherical cap to the area, basically, of the cap, and now you regard the supremum. Which, of course, if you just have a bound on this, you can just plug it in the previous one, here, right here, and then you integrate, normalize, and basically also bound. Okay, now this is basically, again, done just for the 2 sphere, but you can be much more general, consider just any metric measure space. You would have a notion of a ball, you would have a notion of an integral, right? So let's do this. So we have a metric measure space, we know what the ball is, basically. We've center W and say height T, where T now runs from 0 to diameter of the space. Might be infinite. Now you can define the LP discrepancy similarly. You just consider this expression. Again, you count how many points fall into your set A, in this case the balls, absolute value, take power P, integrate, right? Or again, replace by the supremum over A. And here I just wrote T, which is basically the test sets that you will consider. Right, in the previous slide, we were considering basically only of spherical caps, but no one says it's a must. You can just restrict yourself to other test sets. This is usually when people are, it's a natural choice basically for the sphere. Right, again, just the supremum. And if you have, say that this infinity discrepancy goes to 0, as n goes to infinity, you would say that this sequence is asymptotically distributed. Now let's give a couple of examples, right? Mm-hmm. So for the 2 sphere, usually there's this paper by Eisleitner, Brauchert, and Dick. They have shown that the spherical digital nets and Fibonacci lattices, if you have n points of those, then they have shown that the spherical cap discrepancy is bounded of the order n to the -1/2. Similarly, the diamond ensemble introduced by Carlos Beltran and Tujueteo, who has shown that the spherical cap discrepancy of the diamond ensemble is exactly of the order n to the minus 1/2. And I think Pedro will be talking about these point constructions tomorrow, so I guess he will tell you more about it. And also with my co-authors Julian Hofstadler, who is a PhD student at the University of Passau with Daniel Rudolph, and Michel Mastriani, who is a PhD student of Dimitri Bilic at the University of Minnesota. We have shown that the spherical cap discrepancy of Hilpig's points is also of the order n to the minus 1/2. So, and there are many more examples, just to, yeah, there's also a paper by Phillips, Lubotsky, Phillips, and Sarnak, and they basically have constructed points on this two-sphere again, using reduced words from rotation matrices. Then I think there's a paper by Jordi Marzo and Mas. They've shown, okay, if you take minimizers of the Rees energy, then the spherical cap discrepancy will decay with some order of n, not close to 1/2 as far as I remember, but still something. And there are also many more point constructions of which the bound is not even known. I think the spiral points introduced by Zhao is such where it's known they're asymptotically uniformly distributed. Right. There's one more example where basically I've been able to show that if you have a perturbed lattice set, so for this talk, what I mean by this is you just have z to the d, you take a factor in front of it, like 1/k, and you just move by one vector, right? In the end, you will always have k-squared elements in your half-open hypercube. And since they're always uniformly well distributed, right, you'll expect, okay, if you have a map from the unit hypercube, say to the sphere, the points will also be uniformly or well distributed on the sphere if the map is nice in some sense, right? So mesopreserving, for instance. Now, one such map is the Lambert projection, and it behaves basically like this. It goes from the unit square to the sphere via this projection. So you take the unit square, you scale it, multiply the height by 2, the width by 2 pi, then you just fold it into it together, form a cylinder, and then you just project inwards parallel to the R2. And this way you
it's called Lambert, not Mercator projection?
There are many names. So yeah. I use basically...
Mercator, it is not Mercator. Lambert is quite much later. Yeah. 200, yeah. 300 is later.
Well,
this is cylindrical.
This the name has been used in this paper. That's where I saw it, so I just used it. Okay. I guess, yeah. Anyways, this projection. Let's call it L for whatever it stands. Now, the theorem that I've been able to show is, okay, well, this is actually just a special case, but it's good enough for our talk today. You just take a factor 1/k, and for just any translation that you put there, doesn't matter if you map your points via the Lambert projection. This Wn will be just a mapped perturbed lattice. Then we'll have a spherical cap discrepancy of this order. It's bounded by 10 over square root of n. So this gives you a big family of points that have a good spherical cap discrepancy. Again, that's the paper. So all these examples that I've shown you have something in common. So first of all, no one has achieved any bound better than n to the minus 1/2. And they're all deterministic. But for deterministic point sets, that's a big problem. Can you show something better? For probabilistic point sets, better bounds have been shown, I think also by Marzo, Beltran, Ortega Selva, just using determinant point processes, for instance. Okay, so we have now shown quite a few point sets that have a nice discrepancy on the sphere, and it usually also just the two sphere. Now the problem is, usually if you use point sets, you want to discretize your manifold, right? Be it for numerical integration, discretization for whatever reason. And if you really want to do numerical integration, say you want to evaluate your function on these point sets. Now the problem with those point sets that I've shown you, they're not progressive. So basically if you take two different n, then the intersection of those point sets is usually empty. Which basically means, okay, if you want to have say a different n, then you would have to evaluate all those functions at all those, this essentially the whole number of points again, which basically means a lot of computations. So it would be really nice I think, if you have something like point sets that's progressive, right? So if you just want more points, you can keep the old ones and you just add the new ones, and then you add the complications for more. And this is basically a sequence, right? So the goal today, that I hopefully will achieve, is I want to show you, okay, there's an algorithm, we can construct a sequence on the two sphere such that the initial segment satisfies that you have a bound on the spherical discrepancy of the order n to the minus 1/2. Okay, that's what I'm trying to do today. And in order to do this, I'll use a rather general theorem and then apply it basically to my previous result on the discrepancy of the two sphere. Now, before I move on, let's perhaps try to find some examples of point sequences on the sphere. Right, it's always nice to show that somebody else was interested in the problem. And if you have big and cool names, it's always a good thing. So there's this paper by Arnold and Krylov. They've shown if you have two rotations, A and B, and now you apply it to some point on the sphere in the following fashion. Okay, you obtain a sequence, you consider x, ax, bx, a squared x, abx, bx, b squared x, and so forth, right? You'll obtain essentially a sequence and also a set. And the result is, okay, if this set is dense in S2, then you know that the sequence is asymptotically uniformly distributed. Again, no bounds essentially on how quickly the discrepancy would go down. And this is the reference. And a second paper that I found came out just in March, basically by Dimitri Bilic, Michel Mastriani, so his PhD student, Ryan Matzke, his former PhD student, and Stefan Steinherberger, a very productive mathematician. I think you have heard of him. I mean, I guess statistically speaking, half of you are his co-authors. Anyway, Ryan will be speaking about this, I think, after the coffee break. So I don't know if you're going to mention something, but they have shown essentially that they have constructed a sequence on this SD spheres, right, with small L2 discrepancy. And these are the only examples that I know of, right? And you see, it's like a 60 years gap, so I don't know, there's not much known, or I don't know, the results are buried somewhere. All right, so hopefully this holds. I mean, it's a work in progress. I basically obtained most of the results on this weekend. So let's see if it's true. So assume we have a projection from the hypercube 0, 1 to D to some measure space M. Now choose any P between 1 and infinity, and the base B which is bigger than 1. And now let's assume we have a sequence of HM points such that for every perturbed lattice set as introduced in base B, the map of this perturbed lattice set is now point set in M. And say we have this integral symbol of this discrepancy to the power P will be bounded by H over M. So that's the assumption, right? We have no assumptions on the map, we don't really care. But what we of course will need is some useful bound, say, for the projection. And we also don't care what the space is, we just need a measure to define this integral symbol. And it's not even an integral, so it's basically a placeholder for something that's sublinear and monotonely increasing in its arguments. But okay, so there's a lot to unravel here. We will construct this sequence as box, and our projection will be the Lampere map. And then we'll just apply this theorem with my previous result, right? This will be just the cap discrepancy for the lattices, and then I will have shown that the sequence behaves like n to the minus 1/2. Okay, so I mean, you can think of this if you like. If you have a metric measure space, you can think of it as the double integrals. But note that I have to renormalize here because I need a fixed function for my result that's independent of m or BDM, or the number of points really. So either you can think of it as a double integral, then what you obtain is this result for the point sequence. You can think of it as the supremum. Again, this is sublinear and monotonely increasing its arguments. It still satisfies the assumptions. So you'll have these bounds. This is, of course, the version we're going to use. All right, so the next and the most important thing is the definition of this sequence S box. So it is in base P and dimension D. And that's the definition. So first step is you choose S0, and I'm afraid I'll initialize the sequence with 0. It's just the origin. Now assume you have defined B to the DM elements. What we do next is for every k strictly between 0 and b to the d, we form this sets, well, we concatenated essentially copies of the previous elements. So hk are vectors. They're in this set 0 to b to the minus 1. We have d copies, the Cartesian product, d times, minus the origin. And this set is basically these vectors in some order, so please. And at the step m, we just scale these vectors and add the previously constructed sequence to it. So it's a pointwise addition to each of those elements. And the short version looks basically like this. Okay? So we just concatenate the previously obtained sequence and increase and define the sequence recursively in this way. So let's do it perhaps for B2 and dimension 1, just to see how it works. So we have the interval 0, 1. The first element is S0 here. So the next element is we take hk, which should be between 0 and 1 to the power of 1 without the origin, which is just 1. And we scale it by b to the m minus 1. In this case, it's 1/2. So we just shift the previously generated set by 1/2. So this is S1. And now we take this constructed sequence, we shift it by 1/4. And this will be S2, S3. Now we have constructed this lattice and we shift it again by 1/8. So this will be S4, S7, S6, and S8. S1, this is 3, sorry. This is 6, this is 5, and this is 7. Okay, this is clear? Also, you might have realized this is the van der Korput sequence in base 2. Again, I think I don't need to do it in base 3. Let's do it perhaps in dimension 2. So it basically looks like this. We start with S0, and now we move, say, up, S1. We move to the right, S2, and we move diagonally, S3, right? And then we have these 4 points. Now we shift them essentially either up, again, and respecting the previous order, or we can just move it to the right, then up to the diagonal, and then up. Okay? This is the most important part, and also we see, sorry, that every time we have a pure power of b to the d, we just fill up the integer lattice. We have a factor of b to the minus m. Right? Any questions to this? No? So that's again the picture. Again, so we'll fill out the lattice. Okay. Right. So the lemma, a very important lemma will be the following. Suppose to take any natural number m, and now any vector of the values 1, 0 to b to the d minus 1, Cartesian product m times, no matter what. Then you can form this function kmt, which basically looks like this. You have these coefficients, and you have powers of b to the d. Now let's say a t equals m. We have m plus 1. This is bigger than the end value, so this is just 0. And we end up with epsilon m b to the dm. And as t decreases, this value increases. Okay? And the claim is, for any fixed t, and for any k less than b to the dt, if we consider this part of the sequence, so we start with kt, and then we go k plus 1 points further, then there is a vector v such that we essentially started at 0 and went to the point k, which basically means, okay, this is just the sequence shifted by some vector. Right? This is the self-similarity of the sequence. Is this believable? So let's see why this might hold. right? Here in the definition, if we just want, what we see is basically, let's go to the picture perhaps. So we have finished one lattice, and then we copy the lattice and move it to the right, right? And we essentially ask, okay, in what lattice are we? We might be in this lattice, so we just have moved this lattice by a certain vector v. So this was the first step. But within this copy of the lattice, again, we just have the same construction, right? Because it's just reiterating itself. All right, so I hope this is somewhat believable. And now if we just plug in k is actually b to the t minus 1, then this is just the initial sequence moved by some vector. And since it's just the initial sequence, as we have seen, this is just now a perturbed lattice. Okay. Right, so now I'm going to prove the main theorem. So every natural number can now be written as this p-adic expansion, where p is now b to the d. And this gives us, of course, some coefficients, as in the previous lemma. And now we define this function k of j and k. Little k. Okay, it's hard to pronounce. Anyways, it looks like this. So let's perhaps take a first look at it. If j is 0 and k is 1, what happens? Then we start at n plus 1, so this sum just disappears. If k equals 1, this is also 0, so it's just 1. And if k is plus 1, then we just go, and j is 0. So if k is 2 and j is 0, again, this is 0, this is 1, and this is b to the dn, right? And in the end, what we obtain is this decomposition. We consider any points at A, and we have now our sequence which we construct in such a way that it's just a projection of our map P to D. Now we use this factorization and pull everything basically together in this way. And as we have seen before, this is now respects essentially just the sequence as it grows. Now we can take absolute values of this expression. Is there something I'm doing? We can take absolute values, and we can use another triangle inequality and move the absolute value in front of this sum. We can also take the pth power. P is bigger or equal to 1, right? So it respects the inequality. Now we can use the Jensen's inequality to obtain a value c to the p, which is just the number of terms that we have, which is just the sum over the aj's, which is just digit sum, to the power p minus 1. And then we have the power of p in the inside here. Right? Now, let's use the previous lemma. So these points, z of k, jk till jk plus 1, right? This is exactly the index is the projection of the points k, jk minus 1. So I'm sorry for this shift, right? We start with S0, and this we call then z1. But from the previous lemma, we have seen that this expression, k, jk minus 1, is just this value, and we just go exactly as far to hit essentially the next power is just the perturbed lattice with this spectrum. Okay, and all we need to do is now we apply our integral symbol, which is monotonally increasing in its arguments, so it preserves this inequality, and it's sublinear, so we can interchange the symbol with the sum. And then by assumption, we have a bound on this expression, which is just the discrepancy more or less of the projected perturbed lattice. So we just plug in here h to the n minus j, and then we're finished. That's the proof. So we have basically shown this bound. And now let's recall previous. Are there any questions? I'll go to first. Okay. And this. So I hope I've convinced you that this theorem holds. Now let's recall this bound that I've obtained in my previous publication. It looks like this. And now from this we will obtain values for these functions hm. So we just multiply by b to the 2m, which is n, and we obtain b to the m, which is square root of n, right? And this is now a function hm. And this holds for every projected lattice, right? So for every perturbed lattice sets, sorry, for projection of the perturbed lattice sets, we have these bounds now. So we can apply this this theorem with Lambert projection or Mercator projection, and we'll obtain that our sequence now satisfies this bound. And now a to the j is just some value because it's the b to the b squared periodic expansion. This is bounded by b squared minus 1. And then we have essentially a geometric power series which we can evaluate as this value. And here we obtain essentially b to the n, which is the square root more or less of the value n, and which shows that the initial segments of our sequence n have a spherical cap discrepancy of order n to the minus 1/2, just by applying the previous theorem. And so this now gives me my goal and finishes my talk. So thank you very much for your attention.
Questions?
Okay. Can you gain to show reference for Arnold, curve of Arnold?
Sure. A bit disappointing that that's the most important part of my talk. But
No, just that's what it is. I surprised that he got it. You found that?
yeah, I googled for sequences on S2 or on SD basically. That's the only thing I found, just 2-dimensional spheres. I mean, it was really buried, so actually somebody on Tech Exchange found it. I followed the rabbit hole in the end.
What is this paper?
It's not a normal paper.
It's just for papers.
Yeah. Because people work on a different sequence of the uniformity. So it works.
But it is a torus actually. I surprised that it's difference. Sorry. Do you know wooden what is it called? Because do you know he
Yeah, sure. There was a postdoc in TU Graz.
Yeah, and he gave a presentation, not similar, but it's about this discrepancy in ICER 5 years ago. Do you explore it? He published that. Not similar. He gave a presentation 5 years ago in ICER. Yeah, 2018 spring.
Okay.
It is actually his presentation was similar to you, but very different. I mean, references. And also he has some sequences, and also he count discrepancy.
Okay, I was not aware of that.
Okay, you have here his host.
Sure, thank you. Thanks a lot. I'll try to find now that I know the author, I guess it's easy to find.
I don't know. So actually that.
Right?
So for these perturbed lattices, whether the sequence version or the point set version, for the square root of n that you're getting, is that just an upper bound, or does that seem to be the best that can be done?
What's the best upper bound? Because there are examples, right? Because take a look at this. Where's the picture? Yeah, just give me a second. Yeah, right. So this is the image, just right, because in the unit square everything is parallel, so this will be parallel. Right? And I just consider a spherical cap. We've sent a north pole, then you have lots of points on the boundary, and it's square root of n many. And then of course this destroys the discrepancy, or a mixing bag. But of course, yeah.
And usually these kinds of sequences, which are usually called layout sequences, by the way, it's layout who started all this whole business. Actually before him it was Erdős, with the idea of adding one point, but some sort of optimization. This is a different procedure, but usually you suffer from large constants, so you might get the square root of it. Do you have any idea, from a practical perspective, what the constant is out there? So
For the sequence, you mean?
the estimate on the, you get a square root of that, right?
Yes.
There's a big O, so you got this B there, right?
Yeah. Which depends on the base that you have chosen. Choose a B2, then you have 3, and then you have, say, a wiggle room of 8.
To the N, so the little n is the number of terms. You're taking your capital N.
Is the logarithm of n divided by.
So the constant is not that bad in that case.
We're saying it's not that bad because it's B.
It can be made 65. Let's put it this way.
65.
Yes.
For S2.
Yes. I mean, I just have bounds for S2.
Yeah, it is also, it is known as a called laminated spherical codes. I know even, what is his name? He was great his name John. Yeah, but third one. John Hankins. Yeah, it is a called laminated spherical codes.
Thank you.
But it is what?
One and two papers.
2 papers, yes. 2 papers. 20, more than 20.
So, is this more or less a general scheme that says starting from such type of construction you can prove discrepancy is less than 1 over square root of n?
What do you mean by general construction?
This says in a very general setting, if you start with a rather well-distributed sequence in the unit square and you project it to the sphere, then you obtain a bound 1 over square root of n for the discrepancy.
For the sequence or the set?
For the sequence.
For the sequence? But for the sequence, yeah, you build your sequence essentially from point sets, right?
Yeah.
It's just like I think a good way to construct this, and then you inherit the same bounds.
Yeah.
Yes.
But the sequence in the unit square has much better discrepancy actually. So
I don't think so. For the two-dimensional case.
So for the Van der Kolk, you obtain a bound like log n divided by n or something.
But this is dimension 1. In dimension 2, it's square root of n. Because we are lattices.
Yes, you have no way, but okay, could be, yeah.
No, it isn't. It's a lattice.
Okay. So.
I mean, I guess that's the reason why people have not considered this construction in hypercubes, right? It has really bad discrepancy in every hypercube, but it has really nice constructed properties that you can iterate stuff. Also, you can use, by the way, this result to prove the bounds for the Van der Kolk sequence, right? You just have a bound by 1, plug it in, it's the log.
Some naive question. It's clear that the lattice does not work well for the sphere. And you even explained that because of poles, for instance. But if you cut it and repair it in a random way, for instance, the main part will be lattice and the rest part will be random. What will we have in this case?
It means basically the question is how much do we want to repair?
Yeah, it's true, but could you remind what is the best way if you consider arbitrary? It's log n divided on n, the discrepancy.
Where?
Oh, in n-dimensional space.
The best that you can show is a result due to Beck. So on the sphere, for instance, there should be point sets that gives you a spherical cap discrepancy of the order n to the -3/4. And there are deterministic point processes which achieve this order with high probability. But deterministically speaking, nothing has been shown better than n to the -1/2. And even the best constant is basically my result here.
I see. If you have no more questions, then the speaker.
I will start thanking for the presentation and thank the organizer for the opportunity to talk here. And Well, I'm very happy of being after Damir and Peter's talk, because I will talk about many things that appeared already, and I hope it's not going to be too boring. But well, I will try to explain some other things, because I will introduce again this point processes with negative correlation, so somehow they tend to separate points from each other, so they behave much better than Poisson configurations, for example. So, and my goal somehow is to try to show some applications of these random configurations, and well, we'll see what we can. But well, I will basically skip the technicalities, and let's forget what's written here, and I will consider a random point process just as we can consider it just a random measure, if you want, or some. So technically, it's you can define underlying probability space, and then it will be like a random. Random variables in that space with values, but well, let's forget about it. The point is that you have this random point process, and well, under some hypothesis that I will just skip, this a random point process in general can be described by something called the joint intensity functions, which are these functions rho in here, satisfying this property. The idea is that this is, well, when they exist, this rho is determined process. Okay, and let's see just one example to see, well, some notation if you want. So, for example, if you consider a set, well, that should be included, of course. So a set included in your metric space. I'm talking here about the metric space, but if you want, we can talk about the sphere all the time, because this is what we're going to introduce right now. So if we have a subset of the sphere, then the number of points, I will denote it like this, so the random point process applied to this set, well, it will be like taking here the characteristic function of the set, and then I will have one function just, and it will be the expected number of points, will be the integral of this first intensity function, this rho 1 in A. Okay, so this rho 1, if you want, is the one sort of giving you in average the number of points on each well, set A. Okay. Okay. Well, this is just. And here I have some pictures I borrowed from this great book by Krishnapur, Perez, and Virac, where you can actually find a lot of information and things, great results about point processes in this sense. So point processes with a negative correlation, so with points that tend to repel each other. So in terms of well, if we look at point process on in R2, and we just consider a window, if you want. So we have 3 windows here looking at 3 different processes with a different behavior. So this will be the Poisson process. So you have some points which are very close to each other, and you have some gaps between, kind of big holes between them. And well, this is even more exaggerated here. This is what is called a permanental point process. So the points tend to be close together. And this is going to be the one we're going to talk about today. Is a point with repulsion. Okay, so this is again random, but they look much better in terms of well distribution. No. Okay, but well, I will recommend this reference for most of the concepts that I'm going to talk about. Okay, but the kind of, so in particular I'm going to talk about something called determinantal point processes. This was introduced already this morning by Peter. And the idea is that in this case, these joint intensity functions, that they have a very nice structure. and well, somehow coming from the physics community, if you want. So the idea is that these intensity functions are going to be the determinant of a given kernel, if you want. Okay, so you have this gram matrix, if you want, and well, it has to satisfy some properties for this to be actually like densities, if you want. But at the end, it's a very simple definition. Okay, so you have this determinant of. So the row 1 we saw just in the first slide. The second sort of controlling the expected number of points will be just your kernel, if you want, in the diagram. Yeah? So this will give you the density, and if you have something like I don't know, you have something constant here, it means that your the average number of points on each set is going to depend just on the measure of the set. No, so it's going to be uniform in sets, and we can say even more about this because, well, for example, something that we can see from here also is that these points already have some repulsion between them, because if you consider here 2 points of this, 2 of these x's are getting close to each other, then 2 of these columns are going to be very similar. Okay, and of course, if they are equal, then the determinant will be 0, and this will banish the density. So this is really stopping the points to be very close to each other. Okay, so this is why they are somehow the model for fermions in physics, and this was I guess the original idea by the person who introduced this, who was Odile Marquis in the 72. Okay, but not with this name, and there are examples of the determinant of point process which have been used for well, much more earlier, but well, she introduced this in the physics PhD actually thesis. But well, I was checking yesterday, for example, on Google, when this determinant of point process word started appearing in the literature, and there's basically nothing until 1998. Okay, so it's quite recent where they, and after that there's just an exponential expansion of this thing, among other things, because they have been used in machine learning, and there are some connections with things which are sort of, well, that, of course I'm not going to talk about that, but well, the point is that we are going to use this for something else. And well, just to have some basic results explaining the theory, here there's this result. Well, this is why there's this huge gap between 2 very basically the same result. Okay? But Sosnikov, I think, started in this work where the things start growing. But okay, this is just saying that this kernel somehow should satisfy some properties to be able to give you such a point process. Okay. Okay. Well, any question, by the way? Well, we saw this harmonic ensemble already, so I'm going to introduce now a particular class of particular determinant of point process. Okay, and this is going to be, because, well, the idea is that if you have here a projection kernel, this will give you a determinant of point process if you want, and the projection I'm going to consider is the following: the projection in the space of polynomials on the sphere. Okay, so and to do that, I will introduce some notation. So, well, let's consider this HL to be the space of spherical harmonics. All this was introduced also by Saab. So, well, I have different notations. The thing is that you have this space of spherical harmonics of degree L. This is the space of eigenfunctions, the span of this space of eigenfunctions, and then you can define, for example, this reproducing kernel, if you want, on the space of polynomials of degree at most capital L, given by these expressions. So just adding this orthonormal basis on each layer HL, calligraphic HL, and you will get this this very nice kernel that, in fact, as Peter mentioned, this is well, it can be written explicitly in terms of some Jacobi polynomial with some normalization and everything. But well, this is a kernel that satisfies our properties, and and defines a determinant point process. And well, it's a projection kernel on this space of polynomials, capital pi L, that maybe the notation appears at some point. Okay, but well, it's just an example, natural example, I would say, of determinant point process. And okay, so you have this number of points. So each realization, you have the dimension of the space. This one mentioned also by Peter. So you can reach this number of points on each realization of this every time you draw this. And well, just to have a picture. So these are 529 points because it's for the kernel of the polynomials with degree at most 22. Okay. And this is giving you this amount of points on S2. These are the ones given by this harmonic ensemble, and these are just uniform points. Okay, so the Poisson or of the binomial, actually, the number of points are fixed. Okay, so you can see again that these are much closer to each other, and that there are more gaps. Okay, so well, allegedly the point and the idea, of course, is that to try to exploit the idea that you have indeed very, well, at least reasonably tools to compute stuff, and the point process seems to behave much better than the other. So let's see what we can do. Of course, you can extend this to other, well, in general, to any manifold if you want. You can consider a corresponding harmonic ensemble. And well, I'm not going to talk much about this because I'm going to focus basically on the sphere. But well, it's not hard to prove due to the concentration properties of the determinant point processes that actually in any Riemannian manifold, these are almost surely uniformly asymptotically equidistributed, as the Poisson, for example, do. Okay? So it's a very nice process. And well, just to give a couple of examples before I introduce my new results. The first will be to minimal energy. We saw quite a lot of applications this day already, but just to be fast about this. Well, this is a list of people working on this particular setting of random points applied to energies, but with a repulsion between them. Okay, so I'm leaving quite a lot of work in other. But, well, and I'm not repeating names, but it's just to have some names in case you want to check some literature about it. But I will focus just on something. So, as Peter mentioned, so you can actually, with some effort, compute the expected number, so the expected energy of something, okay, of n points given by this random point process. And you can get something like this. No? So you have the number of points n, then the expected number of points will look something like this. And well, the point here is that just as an application, in fact, it's possible to see that, well, a problem that he actually mentioned again, that well, this holds just for this n, but it's possible to, well, if you worst the constant, it's possible to show that actually for any n, the minimal energy is bounded by this, because always the minimal energy is going to be smaller than the expected energy. Okay? So it gives you, for example, bounds for expected energy, and in this case, this coincides with, well, in order, I mean, not the constant of course, but the order matches the lower bound proved by Gohar, Hardin, and Sarf in this singular case. So you have this order behavior. Okay? Well, this is just an application of this. I work with Carlos Beltran and Kim Ortega. Another application that perhaps maybe mentioned and support someone is this about minimal discrepancies. Because, well, it was proved by Beck, but of course not using this jargon of determinant point processes, but using something that at the end has been shown that is a point process of this kind. He proved that there are, well, he proved two things. The first is that any configuration of points on the sphere has a spherical cap discrepancy bounded below by this quantity, the square root of this. And he managed to find nice configuration such that it satisfies this other inequality. Okay, so there's a logarithmic gap here that it still has to be solved. So as far as I know, no one knows what's the right, or maybe there's something in between. I don't know. But well, it's pretty close. So it's this square root of logarithm far from the truth. And in order to prove this, of course, to get an upper bound, so to get a lower bound is much more difficult, but to get an upper bound is a matter of finding examples. And this is why these determinant point processes are useful, because they give you examples that you can actually compute. And this was exactly what he did. So you see, he considered a random configuration, and well, he has to estimate this variance of the number of points again, that it will appear at some point. So this computing variances of number of points on spherical gaps, and then applying some concentration results. In his case, this Bernstein-Chernoff inequality, he got this upper bound. Okay. The point is that, as I was mentioning in this work, actually you can see that well, the kind of point process he was using is this jitter sampling, has been also mentioned, and it's not difficult to see actually that this is a particular example of determinant point process. Okay, and in fact you can actually get this if you want in a row without constructing any area regular partition or whatever. This was done, for example, by Ali Shahia and Thamani. So in the case of the sphere S2, you can consider something called the spherical ensemble. This is a particular case of, so this is a particular determinantal point process that comes somehow from matrix theory. So if you have a matrix A and B, n times n, well, that's the one, with entries, independent complex standard entries, and you consider the eigenvectors of this n minus 1b, so the common eigenvectors, if you want. This turns out to be well, these are in the plane. But if you map this to the sphere through a spherical projection, they look really very well distributed. They are nicely distributed, and they are the spherical ensemble. Okay. For example, in the case of the sphere, actually the density, if you want, of these points mapped through this stereographic projection is actually this quantity. So it's like this sort of van der Waals. Well, there's no van der Waals, but it's given by the sphere.
I think it's squared.
Yeah?
I think the distance squared.
Well, maybe. Let's write the square. Half the square. Okay. Yeah, maybe. Well, in any case, it's something we will recognize as something useful. So it sort of avoids the points to be close to each other, and it's nicely. Well, the point is that using this determinant point process, for example, they were able to get actually this result, essentially using now the idea that you are already with this determinant point process. So it can be seen as an example of application of determinant point processes. Okay, if you want. Okay, but the thing I wanted to talk about today was another problem. The idea of using this or how this behaves in terms of integration. So in terms of numerical integration, okay? Because it's quite natural. Well, we are trying to. So for example, we have this Monte Carlo procedure, if you want, where you have some manifold or whatever. So let's concentrate on the sphere. So we take n points, this time uniformly. Okay? This is not determinantal at all. So this is more like this Poisson. So the points are not so nicely distributed. But well, what you can prove, for example, it's the expected number of this average will be the integral, then the variance of this same quantity is going to be this L2 norm, and well, something that you can show just this bounding this by the square root of the variance, you will get that this error, this error in the integration, if you want to call it, decrease like this. So it's a square root of n. Yeah. So this is what you will get just well, for free applying this Poisson. Okay. then it's quite natural to think what's going to happen, or well, try to see what's going to happen with these other determinant point processes. As we know that at the end they are well nicely distributed uniformly, so they integrate at least one. Okay, so it's a reasonable thing to try. And this was actually an idea of Bardenet and Hardy, who tried to compute all these things in this. In the case of some orthogonal polynomial ensembles in the unit Q, okay? And they obtained this result, okay? So this error was decreasing like this, okay? So it's better than in, well, this was expected, and than in the Poisson, okay? And our result is basically, well, it's a work in progress, and we are trying to extend this to other settings, because basically the point is that we are going to see that this result essentially is all known already, but with different in different places it has been appearing. But it's just an instance of something we have been proving, and the important thing or interesting thing I think is the waiver, and because well it's also written in the case of this harmonic ensemble, but we can apply it to other settings. Okay. And but well, the point is that the result is well, this is a joint work with Matteo Levi and Ortega Serra again. And the idea is now the gain is this. Okay, so now before we have this square root of n, now we have n plus 1 over d as they got. And essentially this follows. Well, this is bounded by the square of the variance. So this follows actually from this. Okay, from the upper bound if you want. And this also follows for free actually from this through a result of Soshnikov, a central limit theorem from for determinant point processes. Okay, so as I don't have much time left. Oh, or is that on?
No, it's because it was many questions for the previous.
Yeah, that's true. But I will skip somehow the technicalities. The idea is somehow to relate the variance with some representation for the norm in a Sobolev space. So this is the idea. And I will show this in a particular case. So let's see if we can, well, as I was saying, so the case t equals 1 is somehow this circular unitary ensemble, and then it's already known that, well, due to work of Johansson, that actually this strong stable theorem implies what I was writing about the variance in the case of dimension 1. Okay, and in general, it has been generalized. I mean, the strong stable theorem to general SD space by Akikioru and Kimin Akikioru quite a long time ago. They don't have the connection with these point processes. There's nothing random there apparently. But I mean, well, you can read on this about this quite a lot in Simon's book about polynomials on the unit circle. So first volume, chapter 6. And okay, the point that I just wanted to stress is that at the end we want to compute the variance, and it's well known that in the case of the determinant point processes, in the case of such functionals, if you want, these are called linear statistics. They have a very nice expression. And this very nice expression can be related somehow to a Sobolev norm. And this is why there's this, actually this limit here. So this is because actually you have this Sobolev norm representation. So it's possible to use some theorem by Bertal-Silvestre where you have to adapt it to the sphere. But to get some correspondence in terms of Sobolev norms, and well, for the lower round, it will be essentially the same. You have this Cagliardo expression for the fractional Sobolev norms. But anyway, the point I will just like to finish with the last slide where is written this last result, where we can actually, as a different instance of this idea, we can actually compute in the case of now rough statistics. So now we are going to, again, back to compute the expected, well, the number of points in a set. Okay? And here we compute the variance of the number of points in a set for this spherical ensemble. And well, the novelty, if you want, is that this has been actually computed already. So what's the limit
of the variance of the random variable number of points divided by square root of n. And it turns out to be this in the case of spherical cups. Okay? But this result is for so-called Cacciopoli sets. So these are sets with measurable boundary and rectifiable. Okay? So these are a much more general setting than spherical cups. The point is that the limit here is the bounded, the perimeter actually of the set, and this due to this Levy spherical isoperimetric inequality is actually equal to this in the case of spherical cups. But it's sort of makes also. But I mean, this is a very general result saying that actually your limit is the size or the length of the boundary. Okay? And well, I will leave here, so thank you very much.
Questions?
So one of the first slides I had a construction of DPPs in the sphere.
Yeah.
I just wonder how you did this. Do you have a CUDA program? Is there a code available somewhere?
Well, there's a code actually that bears the name of this of the book. So they describe an algorithm. Oh, there's a delay. No, you told me.
Something.
Oh.
Perhaps good close.
Let's just tell me when.
One of the first.
One of the
You said one of the first. No.
Yeah.
Well, let's go to the one in the pictures, and then we'll see the name of the book.
Which one? No, I'm.
Maybe I'm doing it.
I'm changing it.
Okay, good.
Just tell me when to stop. And
Go to the first. Well, the point is that there's an algorithm there. We programmed the algorithm, and it's described in the book. So
this?
Yes. No, the program. So it's just the standard algorithm as far as I know. So in fact, 2 days ago, Bardenet published a paper in this. Well, put up a paper in the archive, trying to explore, because of course the drawback here is that these points are much more difficult to generate than Poisson processes. Okay, this is so I'm not going to cheat here. Right. So it's not the same. But they think, well, they start working in the idea that as this quantum computers are good to generate fermions, they can be, and this is somehow the underlying idea behind the model of fermions. It seems that they start doing some computations with this quantum computers, and then they say that the future of numerical integration is going to be through this, and because of course this will beat the Poisson. But well, this is at a very earlier stage. But well.
Nobody will ask them in 5 years.
Yeah.
Thank you.
More questions? Yeah, if not, then the speaker.
I wonder if you can have conference picture here.
Ryan Muskin, please.
Good afternoon, everybody. Hope you've all had a chance to wake up a little bit. If not, maybe just shake out. You have one talk left, and then you can go and rest if you need to explore. But I just ask for a bit of your time and attention for this. So the results I'll be presenting involve work that I did in collaboration with my PhD advisor, Dmitry Bilik, his current student, Michel Mastriani, and Stefan Steinerberger. A fair bit of what I'm going to talk about, well, everything I'm going to talk about is just on the sphere and involving Riesz kernels, but many of the results I'm talking about either have been or can be generalized to a variety of other kernels or spaces in one way or another. But for simplicity, we're just looking at spheres and we're just looking at Riesz kernels. So by Riesz kernels, I mean taking the Euclidean distance between 2 points raised to some power, and then basically multiplied by 1 over whatever the power the negative power that you're taking it to. This makes it so that we always have a kernel that's a decreasing function of distance. And in the case where you would take the 0th power, instead you take the logarithmic kernel. we can define for any probability measure on the sphere the continuous Reese energy as just the expected value of the interaction between two IID particles distributed with respect to your measure mu, or alternatively the electrostatic potential energy you get from some charge distribution on the sphere with respect to your kernel. With such kernels, the interesting question, first question would be what kind of measures minimize said energies, and either from classical potential theory or from the 1950s, a result by Bjork, we know that if S is greater than or equal to -2, the uniform measure on the sphere minimizes the Reese energy, and in particular, if S is greater than -2, it is the unique minimizer. Of course, you cut off at S being equal to D, because at that point, every integral that you would take would just give you infinite energy, so it's not an interesting question to try to minimize the energy. We also can, of course, define a discrete energy, where instead of thinking of a charge distribution, electrostatic energy, this is more of thinking of a collection of electrons. Electrostatic energy. So it's just the sum of pairwise interactions between particles for whatever point set you have. And once again, the question that you start out being interested in is, for a fixed number of points, what is the minimal energy and what point configurations would give you said energy? These questions are incredibly difficult to answer fully. So instead, a first step towards any of that, or a different question to ask, would be what happens asymptotically as your number of points gets very, very large. And from a collection of results, it's known that for, once again, S greater than 2, if you have a sequence of point sets, the increasing number of points as you go along, each of which minimizes the discrete Reese energy, then the sequence of point sets is uniformly distributed. In other words, if you take the point sets corresponding discrete probability measures, they converge in the weak star sense to the uniform measure. I will point out that here we can go into it does make sense to ask these questions about the case where S is greater than or equal to D, because you're still getting finite energy here. So we have that if you have a sequence of minimizers, they're uniformly distributed. However, any sequence of uniformly distributed sets as the number of points goes off to infinity will give you the same first order asymptotics for energy. So first order asymptotics for energy don't really give you a good way of distinguishing better sets from maybe ones that are a bit somehow more uniformly distributed. So ideally, one might want a better way of measuring regularity, and the possibility of doing that is through the second order asymptotics of your sequence of point sets. So mathematics is, of course, a team effort, and so from a variety of results that spanned over 2 decades, it is known that for dimension 2 or greater, again, S between -2 and D, we have that the second order asymptotics of the minimal Reese energy are of the order n to the 1 plus S over D. Or in the logarithmic case, the second order asymptotics are of the order n log n, and in that case we actually know the explicit coefficient in front of it. Very quickly, I just want to point out, for just keeping track of things, when S is negative, the Reese kernel itself is negative. So when you see this expansion, the first term here is a negative term, and then we get a positive term, whereas when S is positive, the first order term is positive, and then the second order term is negative. It was mentioned earlier, but the conjecture is that there's actually an explicit coefficient for the second order term for these energy asymptotics. This is still a conjecture yet to be solved. Right, so the idea from this is, as I was saying before, if you have a sequence of point sets and their energy asymptotics behave somewhat along this range, right? The second order term has order 1 n to the 1 plus s over d. It probably has some nice regularity properties, and in fact, in a number of cases, this is something that is very much known. There's a wide variety of different. There's a wide variety of other methods of measuring either good behavior or some kind of regularity that all connect to Riesz minimization. So, for instance, in the case where s is -1, which is basically the same as summing up Euclidean distances. Minimization of the Riesz energy, or maximizing the sum of Euclidean distances, is the same as minimizing the L2 spherical cap discrepancy. You might remember a bit of that from Damir's talk. It also is equivalent to minimizing the worst case error of the numerical integration over a certain Sobolev space. That was a relatively recent result by Brauhart and Dick. In the case where s is d minus 2, which from Peter's talk, you may or may not remember, and this was more he was mentioning for the projective spaces, but for the sphere, this is approximately the same as the green kernel. Not the exact same, but they have very similar behavior. In this case, due to recent results of Jordi and his collaborator, and Stefan Steinerberger, having optimal Riesz energy asymptotics is the same as saying that the discrete measures corresponding to your point sets converge to the uniform measure in the Wasserstein 2 distance at the optimal rate of convergence. In the case where s is equal to d minus 1, so this is right, the Newtonian case. If you think of the dimension just being 2, then right, this is just 1 over the Euclidean distance, the standard thing that you come across in physics. Point sets that minimize the energy have been shown to be useful for interpolation. These are things known as Fekete points, or if you do sequences instead of point sets, they're Leia points. Finally, the two last things is that if s is sufficiently large, it's been shown that point sets that minimize the Riesz energy are well separated. This comes from a combination of results, and then finally, and this is beginning to connect it to one of the briefly connected to one of the topics in the title of this conference. As s goes to infinity, Riesz energy minimization becomes a problem of best packing on the sphere. So hopefully I've convinced you that lots of fun connections, interesting to look at energy minimization. I appreciate Peter's talk earlier today to help introduce some of it, so hopefully you're all a little bit familiar already. And now I'm going to jump to something a bit different, which I have to thank Ed for introducing yesterday, but still good to review. So for any finite point set, we define the polarization of that point set to be the minimum of the sum of interactions between the elements of your point set and some other point on the sphere, and you minimize that extra point on the sphere over any position on the sphere. And this is a quantity that we would be interested in maximizing over all n-point sets. Instead of thinking of it in terms of electrostatics, the way to think of these polarization problems are, imagine you have n light sources on the sphere, and you want to make it so that the least illuminated point on the sphere is as bright as possible. And so just as with energy, as s went to infinity, we get a packing problem. With polarization, as s goes to infinity, we get a covering problem, sort of making polarization a bit of a dual to energy minimization. Of course, just like with energy, there is a continuous version of polarization where instead of taking a sum and maximizing over point sets, we replace the sum with an integral, and we maximize over all probability measures. And a recent, somewhat recent, we're getting closer and closer to 2 decades, I guess, by Farkas and Naj, I hope I'm pronouncing that name right, showed that in the range between, once again, -2 and D, the uniform measure maximizes this polarization, and in particular, if your S is greater than -2, it is the unique maximizer. Right. So, just as with the energy, basically you can then show that from knowing what happens in the continuous setting, you can then show that for S between -2 and D, that if you have a sequence of polarization maximizing sets, that they are uniformly distributed. And in fact, this result extends to the entire hypersingular range as well. And there's once again a combination of results put together to get this. And once again, just as within the energy situation, first order asymptotics do not help you distinguish between different sequences of uniformly distributed point sets. They all end up having the exact same first order term. So once again, the thought would be that just like how second order asymptotics for energy seems to be a nice way to better measure regularity, this would hopefully also be the case for second order terms in the asymptotics for maximal Riesz polarization. And so this is where my collaborators and I come in. We, in the last year or so, were able to find some bounds on the second order asymptotics of maximal Riesz polarization. For an upper bound, you'll notice that in all cases, we have some negative constant times n to the S over D, which, as far as the lower bounds are concerned, we have a match exactly when S is in the singular range between 0 and D, but we start getting other things when we go outside of that range. So in the logarithmic case, instead of just having a negative constant, we have a negative log n term. And in the case where S is negative, we have a negative constant and then a positive term of order n to the S over D. What we believe is that these upper bounds are the correct order and sign for the second order asymptotics. And a bit of that reasoning will show up a bit later in the talk. And so something that would be interesting to do is see if there is a way of pushing up these lower bounds. Just for a quick comparison, looking back at the second order asymptotics for energy, you'll notice the fact that basically going from energy to polarization, you basically lose just a factor of n in your second order asymptotics, at least for the upper bounds, and that for the negative S case, you have this switch from a positive coefficient to a negative coefficient. The loss of a factor of n comes from the fact that instead of doing a double sum, you're just summing once, whereas the change in sign here seems to come more from just certain behavioral properties of energy versus polarization. So now just a bit of a sketch of where all of this is coming from. So for the lower bounds, we actually make use of our knowledge of energy. So again, a result of Farkas and Nagy shows that you can bound maximal Riesz polarization for endpoints from below using minimal Riesz energy for n plus 1 points. The idea of where this n plus 1 is coming from is that if you're doing polarization for n points, then you have n points plus one extra one that you're minimizing its position over the sphere. So this is why we're having n plus 1 on this lower bound. And so we can just take what we know about the bounds for the second order for the asymptotics of the energy, and we immediately get we immediately get a lower bound on the maximal polarization. So of course you always get the first order term, but then what you have remaining is you have some constant term. You get some term of order S over n to the S over D, and then you get some lower order terms beyond that, or in the logarithmic case, you have a log of n term. And this is a bit of, in the case where S is negative, the constant term that you're getting from here overpowers the n to the S over d term because, of course, it has a negative exponent, and so right, decays off to 0 as n goes off to infinity. But so that's where the lower bound is coming from. As for the upper bound, we use a different fact, and that is that the normalized discrete maximal polarization is bounded from for any number of points will be bounded from above by the maximal continuous polarization, which is just what you get from the uniform measure, and is also equal to the minimal Reese energy, which you also get from the uniform measure. This tells us that this difference here is positive, and because we're subtracting our discrete polarization, instead of becoming a max-min problem, things flip, and we now have a min-max that we can pull outside of the difference. Then we can bound this maximum from below, since we know it's positive, by an L2 average, where here I'm just simply rewriting the Reese kernels as functions of inner products instead of Euclidean distance. This makes working on the sphere significantly easier, and just as a way to express different things. I will also point out that this first term here, since these Reese kernels are rotationally invariant, integrating once with respect to the uniform measure is the same as integrating twice. So here, this is just the minimal Reese energy, just written slightly differently. How am I doing on time?
I think we're rather well. Even according to schedule, we have 10 minutes.
Okay, fantastic. So now what would be nice is to have some kind of lower bound on this L2 average. And so for that, we make a use of a relatively recent result from my PhD advisor, Dmitry Bilik, and his collaborator, Feng Dai, basically saying that you can bound such an L2 average from below by the minimum of the absolute value of the first some number of Gegenbauer coefficients in the Gegenbauer expansion of your function. Believe that these were introduced earlier in some of the earlier talks. So the nice thing that happens with that is that the Gegenbauer coefficients of the Reese kernels are all positive, and the nth coefficient is always something of the order n to the s minus d. So what this then tells us is that basically the minimum over here happens when we take the largest lowercase n we can take, which is going to be of order capital N, so the number of points to the 1 over d, and this then gives us our upper bound on the asymptotics of the maximal Reese polarization. Right, so this is just where the two bounds are coming from. Now, I imagine some of you in the audience have noticed that some of the slides I've written earlier all talk about dimension 2 or greater, and maybe you're only interested in the circle. It's a great space. One dimension is a fantastic space to be working in. Do not worry, I have some slides for you. So, looking at polarization on the circle, we first just looking at a few previous results to build up to where we want to go. We have from 2007 a result, the universal optimality result of Kahn-Kumar, which basically says that for s greater than -2, the roots of unity are the unique minimizer of the Reese energy. And then 6 years later, Ed with his collaborators Hartman and Kendall showed that for s greater than -1, the roots of unity are a maximizer of the discrete Reese polarization. And in particular for s greater than -1, these are the unique maximizers. Unfortunately, the methods used for this result don't seem that they can be extended to the range between -1 and -2, but we believe that the statement itself should extend to the range s greater than -2. Now, So now I want to talk a little bit about what's happening in terms of for second order asymptotics of Reese polarization on the circle. To build up for that, we need to talk a little bit about what the asymptotics for energy. So for S between -2 and 1, we had Brauhard, Harden, and Saff were able to find an exact asymptotic expansion of the minimal Reese energy on the circle, which is just the Reese energy of the roots of unity. And so in the non-logarithmic case, just a second order term, of course, of order S plus 1. And actually the result lets you know even lower order terms, but for the, what?
All the terms.
All the, yes, all order terms. You could be, you can go, but for the purposes of this talk, I'm just going to stop at the second order term. And in the logarithmic case, the second order term is just the same as it was before, negative n log n divided by the dimension, which is 1. You'll notice the first order term is missing. That's not a mistake. In this instance, the minimal continuous logarithmic energy is just 0. So that's what happened. That's what happened to the n squared term. So to work our way towards asymptotics of polarization, we make use of the fact that if S is greater than -2 and you have n roots of and you have the nth roots of unity, the locations where you find the minimal potential are exactly in the middle of the arcs between consecutive points, which themselves are just 2 nth roots of unity. So we can rewrite the polarization of the n roots of unity as a difference between the energies of the 2 nth roots of unity and the nth roots of unity, both of which we know the asymptotic expansions for. And so recently written by Lopez Garcia and McCleary, we have that specifically for the roots of unity, the asymptotic expansion of the Reese polarization is given here. Once again, first order term of order n, and then second order term of order n to the s. With the coefficient in front of it, I should say this is, of course, the Riemann-Zeta function. The coefficient in front is set up in a way so that no matter what your value of s is, it's always something negative. And then for the logarithmic case, you just get negative log 2. Here also, just as in the energy case, the first order term just has a 0 coefficient. So that is why you do not see it there. So from the, oh, no, that's the wrong way. From the 2013 result of Harden, Kendall, and Saff, we know that this then is saying exactly, this is a result for when S is between -1 and 1. This is an exact result for the maximal Reese polarization since the roots of unity are optimal. My collaborators and I were able to use this fact as well as the upper bound I showed earlier for higher dimensions, which also works in this case, to be able to show that there was an upper and lower bound where the second order term was both of order n to the s with a negative coefficient in front, showing that we actually know exactly what the order of the second order asymptotics of maximal Reese polarization are. And the nth roots of unity certainly fit within this regime, so kind of gives a bit more of a indication that they probably are optimal, and they just one has to find a way to prove it. How am I doing on time?
You still have 3-4 minutes. Yeah.
Oh, okay. So a quick little bit of an application of that. So not going to go into quite as much detail, but it can be used for, so as Demir was saying in his talk, instead of looking at energy of point sets, well, for him it was discrepancy, but here I can say instead of energy of point sets, you could ask about energy of point sequences, where you of course would expect something to be lost because you're not choosing the optimal set at every number of points, but numerically speaking, it might be very handy because if you were, say, doing some kind of gradient descent, you would have put down n points, and when you put down your n plus first point, you're just doing a gradient descent on a single point to try to find where you get a minimum. So we studied greedy sequences for Reese energy. So just fix some arbitrary initial point, and then for every point after that, you just place it by finding a point that minimizes that minimizes the potential of the first endpoints. And that's just something that satisfies the polarization of those endpoints. Once result by Lopez Garcia and Saf shows that if S is greater than -2, any such greedy sequence is uniformly distributed. And my collaborators and I were able to find some bounds on second-order asymptotics of these greedy sequences. In the case where, I'm not going to get into everything, but we will point out something that was very fun, is that in the case where S is positive, so the singular case, we were able to find that the greedy sequences have exactly the second-order asymptotics, at least in terms of order, that you would want. That the second-order asymptotics are of order n to the 1 plus s over d, suggesting that this is actually a very good sequence to use to distribute and find Reese energy for. And the trick that we use to be able to find such an upper bound is basically at each step when you're putting down a point, you're just taking a minimum. So this is just polarization. You can bound it from above by maximal polarization, and from our earlier results, we have an upper bound on that. And it's just simple. Then this is just some simple addition then to get the upper bound, and our lower bound just comes from the general lower bound on energy. And yeah, I think I'm about out of time, so just some open questions are, it would be great to improve the lower bounds for polarization when the upper and lower bounds weren't matching. It'd be great to find out if the roots of unity are indeed optimal for polarization on the circle when S is between -2 and -1. I don't think that there's been much study for polarization when S is less than -2. So that could be something that would be interesting. I don't know if there are connections for polarization like there are for energy to the same extent, and that would be interesting to see. And then the last two have to do with if I had more time to talk about greedy sequences, but I will skip that for now. Thank you very much for your attention.
Questions?
Had some numerical experiments, there's some pictures that you show us.
There have been some numerical experiments. There are pictures I can show you. They are not on these slides though. Basically, it's do you mean but just numerical experiments for the greedy algorithms? Yeah.
Is this something that operates quickly on a computer, or is it taking forever?
I think it operates quickly, but it technically doesn't produce a greedy sequence. It produces something that's meant to be an approximation of a greedy sequence. Basically, instead of picking the best point at each step, what happens instead is we put down some number of random points on the sphere, and then basically choose the best one out of that, and let that be the next point. And you just do that at each step. So you actually might get something that could be very far off from a greedy sequence depending upon how they distribute in the moment you sample them, but probably it's a good approximation.
Yes, so this procedure, putting points at random, choosing the best one, do you spread the points in some way, or is it just fully random?
At the moment,
out of n variables?
Fully random at the moment. We didn't go too far into numerics. It was just to get some intuition, and that was more in the negative S range because S equals -1. That then connects to L2 discrepancy, and that was really what we were looking at the numerics for, to see how bad or good our upper or lower bounds were. So actually, this is something that one of the open questions is about. Can we find numerical processes or algorithms that are approximately close to a greedy process that would have really good asymptotics? Because seemingly that might mean that we have a really great way to just generate explicit point sets that don't involve just starting out with something random as much.
Yeah, sure.
Well, you write here these connections with what connections are you thinking about?
So I'm actually very new to polarization, but I mean, so for Reese energies, right, I had a whole slide where knowing that you're minimizing Reese energy connects to minimizing L2 discrepancy or minimizing Wasserstein distance to the uniform measure, or it gives you good points for interpolation. I don't know if such connections have been found with polarization. I don't know if they're there, but if people had ideas or aware of them, that would be fascinating to find out. That's more of just a question rather than an open problem because I can't give any direction on it.
Thanks. More questions? If not, thanks, speaker again. And as I'm right, it's you all at 7.
Fair.